Hey guys, good evening, and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Quickly, let me know in the chats. Yeah. Am I perfectly audible, visible? Yes. Welcome back, my dear students. Welcome back. Why is this stuck? Let me check it out. Why is this stuck? Just give me a second, guys. Oh my God. I don't know why it's stuck. Just second. Okay, you tell me in the chats, am I perfectly audible, visible to everyone? Yeah? I need some fire emojis in the chats, people. I need some fire emojis in the chats. I need some fire emojis in the chats. Yeah? I hope I'm perfectly audible, visible. I hope I'm perfectly audible, visible. All right, all right. Yes, I can check it from my phone. I think I'm perfectly audible, visible, but something is wrong here. Just give me a minute. Just give me a minute, people. Just give me a minute. Just give me a minute. Why is Arijit Singh coming here? Something is wrong here today. I don't know. Just a second, people. Just a second. Sorry for the glitch. Okay, let it be. Let it be. Okay, once again, I'll check the chats from my phone itself. Just let me know quickly in the chats again, people. Can you all hear me? Am I perfectly audible, visible? Say yes or no in the chats, quick. I want everyone to say it, quickly. I want everyone to say it quickly, quickly. I want everyone to say it so that I get to know that I'm perfectly audible, visible to every one of you. Thank you so much for the birthday wishes, for the belated happy birthday. Thank you so much. Well, it was on 6th April. On 6th of April, I turned 30. My God. Yeah. Do I look 30 though? Do I look 30 more or less? What do you say? What do you say? What do you say? Do I exactly look 30? More than 30 or less than 30? I just want to know it from you. No, don't lie. Don't lie. Don't lie. Don't lie, people. All right. Perfect. Perfect. Chalo, that made me happy. Huh? That made me happy. Someone is saying cake for us. Yeah, why not? Am I supposed to give you the cake or you are supposed to send me the cake? Huh? Tell me that first. Tell me that first. Okay. Nice, guys, nice. So I hope you know that uh, today we are going to do the class 11th inorganic chemistry. Okay? Complete class 11th inorganic. Right? And my dear students, before starting this particular session, let me tell you, from your class 11th inorganic chemistry, there are almost like 8 questions asked every year in your NEET examination. Okay? Almost 8 questions are asked every year. And I'll try to cover each and every concept from where questions are asked when it comes to your NEET examination. Okay? I'll try to cover each and every concept. So don't worry about that. Everything will be started from the basics only. A lot of people are asking whether we can watch the session if we are starting now, if we have not prepared yet. You don't need to worry. I'll be starting every single thing from the basics only. Okay? And my dear students, today's session is not going to be exactly for 12 hours because class 11th inorganic chemistry, it's a small portion only. It's not that big. So I think we'll be done in like maximum 6 hours. We'll be done in maximum 6 hours. So who all are going to be with me for these 6 hours? Tell me that first of all in the chats. Tell me that in the chats first. Who all are going to be with me till the end? Today just for 6 hours. You're not going to stay with me for like 10, 11 hours today. I want to know. I want to know the honest answer, by the way. Okay? I want to know the honest answer. I want to know the honest answer. I want to know the honest answer, people. And I can see there are almost like 1100 students watching us live, and not everyone has liked the session. Yeah? That is really injustice. So make the like count very high. Smash that like button right now. Right now means right now. I'm checking from my phone. Yeah? Why this injustice, people? Why this injustice? Yeah, now you are behaving like good guys. All right, one more thing. Somebody is asking about the P block. P block is there in class 12th inorganic. Okay, that won't be discussed today. P block is there in class 12th inorganic. Today, I'll be discussing class 11th inorganic chemistry. Perfect. And please, I would want you guys to be with. I would want you guys to be with me till the end. Okay, because for sure, my dear students, everything is going to be crisp, right? Everything is going to be to the point. Whatever questions, whatever concepts are asked when it comes to your NEET examination, all the concepts I'll be touching here. All the concepts I'll be touching here. Perfect. And I will be starting with the most important chapter of your inorganic chemistry. That is your chemical bonding. Perfect. So before starting the session, tell me, are you guys done with this particular part? Are you guys done with this? Yes or no in the chats? Are you guys done with this? Yes or no in the chats? All right. And one more thing. The handwritten PDF of the today's session, I'll be sharing on my Telegram. You know it, right? Like the last time I shared the handwritten PDF on my Telegram, in the similar way, the today's PDF also I'll be sharing on my Telegram. And if you are not the part of my Telegram channel yet, be the part of my Telegram channel as soon as possible. The name of the Telegram channel is Wassim Bhat Chemistry Official. WASSIM Chemistry Official is the Telegram channel name on which I keep on sharing the handwritten PDF, number one. And after every marathon, I keep on sending you the DPPs which you will be solving. Okay? Are these marathons enough? Yes, these marathons are enough when it comes to your NEET examination, guys. Don't worry. Periodic classification chapter also will be done. Don't worry. Periodic classification chapter also will be done. Don't worry. So, my dear students, should we start the session? Fire in the chats, everybody quick. Should we start the session? Fire in the chats right now. I want the Josh to be high like the last time. Okay? I do not want you guys to sleep in between. I do not want you guys to be inactive. Okay, I want this session to be very, very, very interactive. Whenever I'll be asking you anything, do comment in the chats at that particular instant itself. Okay, that's how it's going to be fun. Otherwise, it's not fun at all. Otherwise, it's not fun at all. One thing I'll assure you, all the questions, whatever questions will be asked from the class 11th inorganic, okay, all those questions you will be getting from the today's session. That is my promise to you. That's my promise to you. Even JE aspirants can also watch it. Perfect, guys. So without wasting any sort of time, let's get going. Let's get started with the chapter, my dear students. And the name of our first chapter, the most important chapter, is your chemical bonding. And my dear students, from this particular chapter, every year, 4 to 5 questions minimum are asked in your NEET examination. Point number 1. Point number 2, this chemical bonding chapter, it forms the foundation of your organic chemistry as well. Okay? It forms the foundation for your organic chemistry as well. If this chapter is strong, your organic chemistry, particularly the general organic chemistry, automatically is going to be strong. Okay? And if there is problem in this chapter, that means there will be problem in your general organic chemistry as well. So make sure that you make this chapter very, very, very strong, because don't think that we are only getting 4 to 5 questions from this chapter. Think in other perspective. Think that your organic chemistry is going to become stronger. Apart from these 4 to 5 questions, your organic chemistry will be getting stronger by your chemical bonding chapter. Okay? Perfect. So my dear students, the first topic that we are going to start with, that is going to be your Lewis structures. How do we exactly draw the Lewis structures of different molecules? This is the first topic which is asked when it comes to your NEET examination. And I'm going to make it very, very, very simple for you. Perfect. Just be with me and listen to every single thing, whatever I'll be telling you in this particular session. Every single thing, my dear students. Let's get going and let's start. My dear students, let's exactly get to know how do we draw the Lewis structures of different molecules first. Have a look. For example, I have got carbon monoxide. I have got carbon monoxide. The first thing, if I'm asking you over here, what is that? If I ask you, how many valence electrons carbon has? You must be knowing your carbon, it has got 4 valence electrons. How many valence electrons oxygen has? You must be knowing oxygen has got in total 6 valence electrons. So if I ask you, in this carbon monoxide molecule, how many valence electrons are there in total? I would say there are in total 10 valence electrons. There are in total 10 valence electrons in carbon monoxide. Now people, if there are 10 valence electrons in carbon monoxide, if I ask you, how many valence electron pairs? How many valence electron pairs will be there? See, 1 electron pair means 2 electrons. 1 electron pair means 2 electrons. So there are in total 10 valence electrons. That means there are 5 valence electron pairs in total. Right? Now, my dear students, let's say this is your carbon and let's say this is your oxygen. Okay? Now, the first thing which I'll be doing over here, I'll be putting a single bond between them. I will be putting a single bond between them. 1 bond means 1 electron pair. I had in total 5 valence electron pairs. Out of 5 valence electron pairs, I've used 1 valence electron pair. I've used 1 valence electron pair. Okay? Out of 5 electron pairs, I've used 1. So how many are left? There are 4 electron pairs left. Now people, if I ask you among carbon and oxygen, which one is more electronegative? Your answer will be oxygen. Oxygen is more electronegative. If oxygen is more electronegative, try filling the octet of this oxygen first. See guys, I'll keep 2 electrons here, 2 electrons here, 2 electrons here. So 2, 4, 6 and 8. So the octet of oxygen is complete. Octet of oxygen is complete, right? Now if I ask you, out of 5 valence electron pairs, how many electron pairs I have utilized? This is 1, 2, 3 and 4. I have utilized 4 valence electron pairs. How many are left? 1 is left. Give that electron pair to carbon. Give that electron pair to carbon. Now if I ask you, Is the octet of carbon complete? Check it out. 1, 2, 3, 4. Octet of carbon is not complete. So how do I complete the octet of carbon? My dear students, for that, let me remove one electron pair from here, and instead of that, I'll put a double bond. Let me do one more thing. Let me remove one more electron pair here, and instead of that, let me put one more bond. Now people, check it out. Check whether the octet of both the atoms is complete or not. Have a look. If you look at this particular oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Octet of this oxygen is complete. Look at the octet of this carbon. 1, 2, 3, 4, 5, 6, 7, 8. Octet of both the atoms is complete. Right? So this is your Lewis structure when it comes to your carbon monoxide molecule. Number 1. Number 2, here only, my dear students, let's exactly get to know how to calculate the formal charge on different atoms. How do you check the formal charge on carbon? How do you check the formal charge on oxygen? Let's get to know that as well. Look, try to understand. My dear students, if I ask you, when carbon is present in non-bonded state, when carbon is present in non-bonded state, how many valence electrons carbon has? At that time, carbon has 4 valence electrons. Minus. Right now, how many carbon has? 1, 2. Just count one of it. 3, 4, 5. Okay. So 4 minus 5 comes out to be how much? Minus 1. The formal charge on this particular carbon is minus 1. If I ask you what is the formal charge on this oxygen, have a look. Oxygen, when present in non-bonded state, has got 6 valence electrons. Minus. Right now, how many it has? 1, 2, 3, 4, and 5. 6 minus 5 comes out to be plus 1. So plus 1 is the formal charge of this particular oxygen. That's how you draw the Lewis structure. That's how you are going to write the formal charges on different atoms as well. I believe this is super clear to everyone. If yes, let me know once in the chats. I'll show you one more example. Let me know quickly in the chats. I'll show you one more example. Quickly, people. Yeah? Perfect. Perfect. Let's have a look on one more example so that it becomes very, very, very clear. Let's have a look on one more example so that it becomes very, very, very clear. My dear students, my first step is to calculate the valence electrons. Nitrogen has got 5 valence electrons, plus oxygen has got 6 valence electrons, but there are 2 oxygen atoms. And at the same time, there's a negative charge as well. If there's a negative charge, add that negative charge here. If there was positive charge, subtract that 1 unit. If there's a negative charge, add that 1 unit. If there is a positive charge, subtract that 1 unit. That's it. So just calculate it. It's 5 plus 12 plus 1. 12 plus 1, 13. 13 plus 5 comes out to be 18. So in total, there are 18 valence electrons. If there are 18 valence electrons, how many valence electron pairs will be there? 18 valence electrons means 9 valence electron pairs. Now, my dear students, understand one thing. You have got NO2. If I ask you among nitrogen and oxygen, which one is less electronegative? Which one is less electronegative among nitrogen and oxygen? I will say nitrogen is less electronegative. The one that is less electronegative, that's going to be your central atom. So nitrogen is your central atom. Okay, because nitrogen is less electronegative than oxygen. Perfect. Now, let's keep one oxygen here, one oxygen, for example, here. What is the first thing I do? Put a single bond here, put a single bond here. Done. Perfect. Now, after putting a single bond, after putting 2 single bonds, that means I have utilized 2 valence electron pairs. Out of 9 valence electron pairs, I have utilized 2. I still have 7 with me. Okay. Now, which one is more electronegative here? Oxygen. So try filling the octet of oxygen. So I'll say 2, 4, 6, and 8. 2, 4, 6, and 8. So in total, I had 9 valence electron pairs. Out of 9, how many I have utilized? 1, 2, 3, 4, 5, 6, 7, 8. So 1 electron pair is left. Give that to nitrogen. Now, my dear students, if I ask you right now, is the octet of this oxygen complete? Yes. Is the octet of this oxygen complete? Yes. Is the octet of this nitrogen complete? No. Why is that? 2, 4, and 6. Okay. So now, let's do one thing. Select any of these two oxygen atoms, remove the lone pair, remove the electron pair. Instead of that, put a bond. It is your choice whether you want to remove it from here or here. The choice is all yours. Perfect. Now, my dear students, check it out. Octet of this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Complete. 1, 2, 3, 4, 5, 6, 7, 8. Complete. 1, 2, 3, 4, 5, 6, 7, 8. Complete. Octet of all the atoms is complete. Now, after completing the octets of all the atoms, it is the time to calculate the formal charge. It is the time to calculate the formal charge. My dear students, formal charge of this oxygen. Oxygen in non-bonded state has got 6 valence electrons. Right now, how many it has? 1, 2, 3, 4, 5, 6. Just count only one here. 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 comes out to be minus 1. So this oxygen has got minus 1 formal charge. Look at this oxygen. Oxygen in non-bonded state has got 6 valence electrons. Minus. Right now, how many it has? 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. So there is no formal charge here on this oxygen. Similarly, if I ask you to calculate formal charge on this oxygen, formal charge on this nitrogen, how do we do it? First of all, nitrogen in non-bonded state, 5 valence electrons, minus. Right now, how many it has? 1, 2, 3, 4, 5. So 5 minus 5 is 0. So it also does not have any formal charge. Perfect. So my dear students, I believe this particular stuff is clear. You got to know how to draw the Lewis structures. You got to know how to calculate the formal charge. I'll take one more example. With that, every single thing will get clear. I'll take one more example. With that, every single thing will get clear. For example, one more simple molecule we have, Cn negative. Okay, Cn negative, one more simple molecule. So first of all, if I talk about the valence electrons, carbon has got how many valence electrons? 4. Nitrogen has got 5 valence electrons. There's a negative charge, so add that. So this comes out to be 10. 10 valence electrons means how many valence electron pairs? 5 valence electron pairs. 5 valence electron pairs. Now you need to adjust these 5 valence electron pairs. See, this is carbon and this is nitrogen. Put a single bond first. Right? Put a single bond first. Perfect. After putting a single bond, which one is more electronegative? Nitrogen. Try filling the octet of nitrogen. 2, 4, 6 and 8. Complete. How many valence electron pairs I had? 5. How many valence electron pairs? I had 5. Out of 5, how many I have utilized? 1, 2, 3, 4 and put 1 here. See, the octet of nitrogen is already complete. But is the octet of carbon complete? No. Have a check. 1, 2, 3, 4. Just do one thing. Remove one of the electron pair from here and put a bond. Do one thing. Remove one more electron pair from here. Put a bond. Perfect. Now the octet of both atoms is complete. You can check it out too. 1, 2, 3, 4, 5, 6, 7, 8. Complete. 1, 2, 3, 4, 5, 6, 7, 8. Complete. Right? Now, my dear students, it's the time to check what? It is the time to check the formal charge. It is the time to check the formal charge. My dear people, formal charge of this nitrogen will be equal. Nitrogen in non-bonded state has got 5 valence electrons. Minus, right now how many it has? 1, 2, 3, 4, 5. So 5 minus 5 comes out to be 0. What about this carbon? Carbon in non-bonded state has got 4 valence electrons. Minus, how many it has right now? 1, 2, 3, 4, 5. So 4 minus 5 comes out to be minus 1. So this minus 1 is the formal charge on carbon. If I'm clear to everyone, let me know once in the chats with the fire emojis. If you can draw any Lewis structure of any simple molecule. Quick, people. Everybody in the chats. Everybody in the chats. Everybody in the chats. Everybody in the chats. Yeah? Then have a look on one more example. With this particular example, every single thing will get clear, people. With this example, every single thing will get clear. Okay? Every single thing will get clear. You have got CO3 dinegative. You have got CO3 dinegative. Now, my dear students, if I talk about carbon, how many valence electrons carbon has? 4. How many valence electrons oxygen has? 6. There are 3 oxygen atoms. But there is dinegative charge as well. So add those 2 units of charge here. How much it comes out to be? 6 3s are 18. 18 plus 2 is 20. 20 plus 4 is 24. So in total, there are 24 valence electrons. 24 valence electrons means how many valence electron pairs? There are 12 valence electron pairs. There are 12 valence electron pairs. Now you have to adjust these 12 valence electron pairs. How exactly you'll be doing that? How exactly you'll be doing that? My dear students, among carbon and oxygen, which one is less electronegative? It's carbon. The one that is less electronegative, that has to be your central atom. So carbon is your central atom. Now there are 3 oxygen atoms, 3 surrounding oxygen atoms. These are the 3 surrounding oxygen atoms. What is the first thing I do? Put a single bond everywhere. So I've utilized 3 electron pairs. Now start filling the octet of most electronegative, that's oxygen. 2, 4, 6 and 8. 2, 4, 6 and 8. Perfect. 2, 4, 6 and 8. Right? Now people, if I ask you, how many valence electron pairs I had? How many valence electron pairs I had? Check it out. I had 12 valence electron pairs. Out of 12, how many have you utilized? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Am I clear? Am I clear, people? Am I clear? If you look carefully, octet of this oxygen is complete, octet of this oxygen is complete, octet of this oxygen is complete, but the octet of this carbon is not complete. This carbon has got how many right now? 2, 4 and 6. So what do we need to do? Just select any oxygen atom. For example, I'm selecting this oxygen atom. Remove the electron pair and put a double bond here. Now the octet of all the atoms is complete. Now the octet of all the atoms is complete. Yeah? Right, people? Now at the same time, if you talk about this particular oxygen, check its formal charge. Oxygen in non-bonded state, 6 valence electrons, minus 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is equal to minus 1. So minus 1 is its formal charge. What about this oxygen? Oxygen in non-bonded state, 6 valence electrons, minus, how many right now? 1, 2, 3, 4, 5, 6, and 7. So 6 minus 7 is equal to minus 1. Right? Talk about this oxygen. In non-bonded state, how many valence electrons? Just a second, guys. Okay. Just a second. There is some electricity issue, okay? I hope this is visible to you. In non-bonded state, there are 6 valence electrons minus how many right now? 1, 2, 3, 4, 5 and 6. So 6 minus 6 is 0. So you got the formal charge on all the atoms over here. I believe this particular topic, that is drawing the Lewis structures and calculation of formal charge, I believe this is super clear to everyone. If it is super clear, let me know once in the chats quick. Let me know once in the chats quick. I'll move on to the next topic. Let me know quickly in the chats, people. Everybody. Yes? Amazing. 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 The next and one of the most important topics. Okay? The next and the most important topic from which question almost, I would say every alternate year comes. That is the question from Fajan's rules. That is the question from Fajan's rules. Have you studied Fajan's rules ever? Just tell me that. Have you studied Fajan's rules ever? Quickly. Have you studied Fajan's rules ever? All right. My dear students, I'll keep it very crisp. I won't give you, I'll just give you that information which is required to solve the questions. And that's super sufficient. No need to go into depth at this particular point of time. You just need to know only those things which are asked in your exam. Nothing more than that, nothing less than that. Okay, so have a look. Have a look, guys. Understand. Understand what I'll be saying. My dear students, Fajan's rules. Fajan's rules. As per Fajan's rules, covalent character. As per Fajan's rules, covalent character in an ionic compound Covalent character in an ionic compound. It depends on two things. Covalent character in an ionic compound. It depends on two things. Number one, polarizing power of the cation, polarizing power of the cation, and at the same time, covalent character in an ionic compound. It also depends on the polarizability, or let me write it separately. Just a second. This is point number one. Point number two. Again, I'm repeating the same thing. Covalent character in an ionic compound. In an ionic compound. It also depends on one more parameter, that is polarizability. That is polarizability of what? Polarizability of anion. See guys, one thing, this polarizing power, it is defined for cations. This polarizability term, it is defined for anions. Now guys, one more thing. I'm writing a term. Polarizing power of a cation. Polarizing power of a cation is directly proportional to the charge on cation, inversely proportional to the size of cation. Just these things you have to remember, guys. Whatever things I'm telling you, nothing more than this. Polarizing power of the cation is directly proportional to charge on cation, inversely proportional to the size of cation. Similarly, polarizability of anion. It is directly proportional to charge on anion, and at the same time, this polarizability of anion, it is directly proportional to the size of anion. If you just remember this slide, my dear students, if you remember this particular slide, you are going to mark all the questions correct when it comes to your Fajan's rules. Have a look on this particular slide once more. Covalent character in an ionic compound, it is directly proportional to polarizing power of the cation. Covalent character in an ionic compound, it's directly proportional to polarizability of anion. Polarizing power of cation is directly proportional to charge on cation, inversely proportional to the size of cation. Polarizability of anion is directly proportional to charge on anion, also directly proportional to the size of anion. Now, as I told you, if you just remember this slide, we are done. How exactly? Have a look. Now you'll directly answer all. Arrange the following in the order of the polarizing power. See, these are the two cations. You have to arrange them on the basis of their polarizing power. Okay? Have a look, people. See, polarizing power is directly proportional to charge on cation. Which cation has more charge? This cation has more charge. More the charge on cation, more the polarizing power. More the charge on cation, more the polarizing power. More the charge on cation, more the polarizing power. More charge, more polarizing power. More charge, more polarizing power. That's it. Okay, that's it. Number one. Arrange in the order of the polarizing power again. Now, these are again the cations. Charge on every cation is same. Now, we have to talk in terms of size. We have to talk in terms of what? We have to talk in terms of size, right? As you know, polarizing power of cation is inversely proportional to size. Lesser the size of cation, more the polarizing power. Now, which cation has got lesser size? Li positive has got lesser size. Li positive has got lesser size, right? Lesser the size of cation, more the polarizing power, right? This is Li positive, lithium, sodium, potassium, rubidium, cesium. Down the group size increases. Lesser the size, more the polarizing power of cation. Lesser the size, more the polarizing power here. Perfect. As simple as that. My dear students, one more thing I would want to tell you over here. Polarizing power is also called as ionic potential. It's also called as ionic potential. And at the same time, polarizing power also depends on effective nuclear charge. In case of what? In case of d block elements. Polarizing power also depends on what? It depends on the effective nuclear charge in case of which elements? In case of d block elements. In case of d block elements. And remember one simple thing. In case of d block elements, polarizing power is directly proportional to the effective nuclear charge. Polarizing power is directly proportional to the effective nuclear charge. Polarizing power is directly proportional to the effective nuclear charge. If you have a look on these d block elements, iron di positive, cobalt di positive, nickel di positive, copper di positive. Do you remember their outermost configuration? This has got d6 configuration, this is d7 configuration, d8 configuration, d9 configuration, right? These are their outermost configurations. Now, my dear students, as you move from left to right, you must have studied somewhere, sometimes, on moving from left to right, here, what happens to effective nuclear charge? Effective nuclear charge increases. And as the effective nuclear charge increases, polarizing power of these cations increase in this order. Okay? Right? Remember this particular point as well. Okay? This is copper di positive. This is not copper positive. So it has got D9 configuration. Right, people? Right? I hope I'm clear. One more thing which you have to remember. When we move from 3D series to 4D series, I hope you know what is 3D series. Scandium, titanium, vanadium, chromium, right? Manganese, iron, cobalt, nickel, copper, zinc. When you move from 3D series to 4D series, 4D series to 5D series, what happens to effective nuclear charge? Effective nuclear charge increases. Z effective. Effective nuclear charge increases. And as the effective nuclear charge increases, polarizing power also increases. Okay, polarizing power also increases. So you need to remember this as well. Let's say you've got zinc di positive, cadmium di positive, mercury di positive. This is the 3D element. This is the 4D element. This is the 5D element, right? From 3D to 4D, 4D to 5D, what happens to Z effective? Z effective increases. And if Z effective increases, polarizing power of cation automatically increases. Okay? Polarizing power of cation automatically increases. As simple as that. Right? Similarly, my dear students, there is something called as polarizability as well. Okay? There is something called as polarizability as well. There is something called as polarizability as well. And as you must be familiar with the fact now, polarizability is defined for anions. And polarizability also depends on two factors. One is charge on the anion, one is size on the anion. Polarizability of anion is directly proportional to charge on anion. It's also directly proportional to size of anion. Right? Perfect. Try to understand. N tri-negative, O di-negative, F negative. These are all anions. Now, which anion has got more charge? Which anion has got more charge? It's N tri-negative. More the charge on anion, more the polarizability of anion. More the charge on anion, more the polarizability of anion. Similarly, P tri-negative, S di-negative, Cl negative. More the charge on anion, more the polarizability of anion. Correct? Correct? My dear students, from this particular slide, I just gave you one slide and I'm just using that particular slide. Where is that? This one. I'm just using this particular slide. Again, have a look on this. Again, have a look on this. Covalent character in an ionic compound is directly proportional to polarizing power of cation. Is directly proportional to polarizability of anion. Polarizing power of cation is directly proportional to charge on cation. Inversely proportional to size of cation. Polarizability of anion is directly proportional to charge on anion. Also directly proportional to what? Size of anion. Perfect. Am I clear with this? Am I clear with this? Just you have to remember this particular slide and we are sorted. We are done. We are done. Perfect. Okay. Okay. Look at this particular question. Look at this particular question, people. Arrange in the order of covalent character. Arrange in the order of covalent character. As I told you, covalent character depends on how many parameters? Covalent character depends on two parameters. One is polarizing power of cation. One is polarizability of anion. right? As I told you already, covalent character is directly proportional to polarizing power of cation. At the same time, covalent character is directly proportional to polarizability of what? Of anion. Rest everything we know. Now have a look, how do I solve this particular question? It's pretty much simple. ZnCl2, CdCl2, HgCl2. If I ask you what is the charge on the zinc here, it's +2. Charge on cadmium +2. Charge on mercury +2. This is Cl -1, Cl -1, Cl -1. See, Cl -1 everywhere is same. So I cannot decide on the base of anion here. I cannot decide on the base of anion here. I am going to decide on the base of what? I am going to decide on the basis of cation. This is zinc dipositive, cadmium dipositive, mercury dipositive. Few minutes back I told you, mercury dipositive has got more polarizing power, right? This is 3D, this is 4D, this is 5D. So more polarizing power. More polarizing power means more covalent character. So this is the order of covalent character. Simple. Perfect. Look at the second one. This is zinc dipositive, S dinegative. Cadmium dipositive, S dinegative. Mercury dipositive, S dinegative. So S dinegative everywhere is same. Nothing to do with this, right? Again, Hg dipositive has got more polarizing power. So hence more covalent character here. Simple. Simple, my dear students. If you look at the next one, this is Li positive, F negative. Na positive, F negative. K positive, F negative. Rb positive, F negative. Cs positive, F negative. So F negative everywhere is same. So I'm not going to decide on the basis of F negative. I am not going to decide as per F negative. So on what parameter I'll be deciding? What is going to be a parameter on which I'll be deciding? Quickly. What is going to be my parameter on which I'll be deciding? Quickly, people. Li positive, Na positive, K positive, Rb positive, Cs positive. Charge everywhere is same. Charge everywhere is same. Right? So I'll be deciding on the basis of size. Lesser the size of cation, more is going to be its polarizing power. And more the polarizing power of cation, more is going to be the covalent character. More is going to be the covalent character. I hope this is clear. This is BeF2. This is here BeCl2. BeF2, BeCl2, BeBr2, BeI2. Look carefully. This is B dipositive, F negative. This is B dipositive, Cl negative. B dipositive, Br negative. B dipositive, I negative. So first of all, cation everywhere is same. So I cannot decide on the basis of cation. I'll be deciding on the basis of anion here. For anions, what do we decide? We define polarizability. Now, charge on every anion is same. Charge on every anion is same. Now talk in terms of size. Which anion has got more size? I negative has got more size. More the size of anion, more the polarizability of anion, hence more the covalent character. So this is the covalent character order. Am I clear, my dear students? Quickly in the chats. Am I clear quickly in the chats? Tell me the answer of all these questions here. You should be in a position. This is Al tri positive, this is F negative. Al tri positive, Cl negative. Al tri positive, Br negative. Al tri positive, I negative. Cation everywhere is same. Talk in terms of anion. Charge on every anion is same. Talk in terms of size. More the size of anion, more the covalent character. Right? Mg dipositive, F negative. Mg dipositive, Cl negative. Mg dipositive, Br negative. Mg dipositive, I negative. Right? More the size of anion, more the polarizability of anion, hence more the covalent character. Simple. What about this one? Li positive, F negative, Cl negative, Br negative, I negative. Again, the size of anion dominates here. Perfect. I think everywhere the answer is going to be the same. Everywhere the answer is going to be the same. Now comes one more point. Now comes one more point. My dear students, remember this particular point. Remember this particular point. I'm giving you the crux of everything. Okay, remember this particular point. Polarizing power of the pseudo inert gas configuration. Polarizing power of that cation. Which has got pseudo inert gas configuration is more than that of polarizing power of that cation which has got inert gas configuration. Now what is pseudo inert gas? My dear students, whenever you see this configuration, that is inert gas configuration followed by D10 configuration. What does that mean? Let's say you have got Let's say you have got first of all copper. Okay. Do you know the outermost configuration of copper? Do you know the outermost configuration of copper? It's argon 3d10 4s1. Okay. This is argon 3d10 4s1. Perfect. Now, my dear students, if I write Cu positive, so take one electron out. Take one electron out. So you have taken this out. Do you see? Look at this particular configuration. This configuration is basically, this is your inert gas configuration from here to here, followed by D10 configuration. Inert gas configuration followed by D10 configuration. What do I call this whole configuration as? This is called as pseudo inert gas configuration. Pseudo inert gas configuration. Remember, my dear students, that particular cation which has got pseudo inert gas configuration, its polarizing power is always more than that cation which has got inert gas configuration. Like you have got sodium. Like you have got sodium. Okay? You have got sodium. What is the outermost configuration of sodium? It is a neon followed by 3s1. If I write Na positive configuration, so take one electron out, taken one electron out. So Na positive has got inert gas configuration. Na positive has got inert gas configuration. This is pseudo inert gas configuration. This is inert gas configuration. And that particular cation which has got pseudo inert gas configuration, its polarizing power is always more. Its polarizing power is always more. Remember this particular point. And if you remember this particular point, I believe you can easily solve this question. Among these two, which one has got more covalent character? I want your answer in the chats now. I want your answer in the chats now. Quick. I want you to let me know the answer of this question. Quickly, people. I want you to know the answer of this particular question. Everybody in the chats. Everybody in the chats. Quick. Let me see how much you are remembering, how much you are understanding. Absolutely. Why you are saying CuCl? Because here the cation is Cu positive. Here the cation is Na positive. Cu positive has got pseudo inert gas configuration. This has got inert gas configuration. And that cation which has got pseudo inert gas configuration, its polarizing power is more. More the polarizing power of the cation, more is going to be the covalent character finally. That's it. That's it, people. Okay, that's it. Now, there are some applications of these Fajan's rules, which you should know as well. Applications of these Fajan's rules, which you must know. My dear students, let me first of all tell you. Solubility of ionic compound. Solubility of ionic compound in polar solvent. You know, it's always more than that of the covalent compound. Okay? Solubility of ionic compound in the polar solvent is always more than that of the covalent compound. Right? Or I can say solubility is directly proportional to ionic character. Right? That means it's inversely going to be proportional to covalent character. Remember this particular point. If you remember this particular point, compare these two, Ag2S and Ag2O. Ag2S and Ag2O. This is Ag positive, S dinegative. Ag positive, O dinegative. So, cation is same. Talk in terms of anion. More the size of anion, more the polarizability. S dinegative has got more size, right? So, this has got more covalent character. So, this is the order of covalent character. So, what is going to be the order of ionic character? I'll say order of ionic character is going to be this. This is the order of ionic character. Okay, this is the order of ionic character. And whatever is going to be the order of ionic character, same is going to be the order of solubility. So, order of solubility here is going to be the same. Right? Order of solubility is going to be the same. So, I would say Ag2S is less soluble than that of Ag2. Ag2S is less soluble than that of Ag2. So, remember this particular point as well. Yeah? I believe I'm clear to everyone. And if I'm clear to everyone, there is one more application, or leave one more application, there is one more example. On one side, you have got FeOH whole thrice. On another side, you have got FeOH whole twice. Perfect. This is Fe tri positive here. This Fe di positive here. OH negative, OH negative. Now here anion is same. Talk in terms of cation. Charge on this cation is more. So this is the order of covalent character. More the charge, more the polarizing power, and hence more the covalent character. What is going to be the ionic character order? Ionic character order is going to be reverse. FeOH whole thrice is going to be less ionic than that of FeOH whole twice. This is the order of ionic character. And if this is the order of ionic character, same is going to be the order of solubility as well. Right? I would say FeOH whole thrice is going to be less soluble than that of FeOH whole twice. Am I clear? FeOH whole thrice is less soluble than that of FeOH whole twice. I believe I'm clear to everyone. If yes, let me know once in the chats with some thumbs ups. Quickly. Quickly, my dear students. Quickly, my dear students. Quickly, my dear students. Everybody. Everyone in the chats. Quickly. Everyone in the chats with some fire emojis. Everybody, people. Quick. Quick, quick, quick. I want the chats to run. I want the chats to run. I want the chats to run. Perfect. Amazing. Amazing, guys. Now, one more thing, guys. One more thing. This is one more application of this Fajan's rules. What application this is? This is application based on melting point. Application based on melting point. Remember the same thing. Melting point of ionic compounds. Melting point of ionic compounds is more than that of melting point of covalent compounds. Melting point of ionic compounds is more than that of melting point of covalent compounds. Or you can say melting point is directly proportional to ionic character and inversely proportional to what? Covalent character. You can say it in simple words. Now, my dear students, what do you have? You have got BeCl2, for example, beryllium, magnesium, calcium, strontium, and barium chloride. Okay, these are the chlorides of your group second elements. Now I have to check which one has got maximum melting point. How do you check it? How do you check it? Pretty much simple. This is Be di positive, Mg di positive, calcium di positive, strontium di positive, barium di positive. Right? Now, lesser the size of cation, more will be its polarizing power. And more the polarizing power means more is the covalent character. Right? So BeCl2 has got more covalent character. That means it has got lesser ionic character. It has got lesser ionic character followed by MgCl2, followed by CaCl2, followed by SrCl2, followed by BaCl2. This is the order of what? This is the order of ionic character. And whatever is going to be the order of ionic character, same is going to be the order of melting point. So this is the order of your melting point of the chlorides of group second as well. I hope this is clear to everyone. Okay? I hope this is also clear to everyone. Similarly, my dear students, one more last application. What is that? It's thermal stability. That is application based on thermal stability. Remember, thermal stability of ionic compounds is more than that of covalent compounds. So you can say thermal stability is directly proportional to ionic character, inversely proportional to what? Inversely proportional to covalent character. Thermal stability of ionic compounds is more than that of covalent compounds. Right? So you can say thermal stability is directly proportional to ionic character, inversely proportional to what? Inversely proportional to covalent character. Now, for example, you have got lithium carbonate, you have got sodium carbonate, potassium carbonate, rubidium carbonate, and cesium carbonate. These are the carbonates of your group first elements. These are the carbonates of your group first elements. Now, if I have to arrange them on the basis of their thermal stability is directly proportional to ionic character. So, talk first of all about the ionic character. This is Li positive, this is Na positive, this is K positive, this is Rb positive, this is Cs positive. Lesser the size of cation, more is going to be the polarizing power of cation. More the polarizing power of cation. That means more is going to be the covalent character. More the covalent character means lesser is going to be the ionic character. So this is the order of ionic character. And whatever is the order of ionic character, same is going to be the order of thermal stability. Am I clear? So on moving from left to right here, thermal stability increases. Perfect. If yes, let me know in the chats. And if this concept of Fajan's rule is clear to you, if you can solve each and every question based on Fajan's rules, let me know once in the chats now so that I can jump into dipole moment. Quickly, people. Everyone quick. Everyone quick. Guys, one thing I'll tell you, this is going to be the smartest one shot of class 11th in organic chemistry. Because this is straight to the point. Okay? Only those things are discussed which are asked in the exam. Okay? That too, crux of it. Let me know quickly in the chats if all these things are clear. Everyone. Everyone, I'm looking at your chats only. I am looking at your chats only. Everybody. Everybody. All right, amazing. Now. Let's have a look on one more important topic. One more very, very important topic, which is frequently asked, and also it is asked from your organic chemistry as well. Okay, so let's try to cover this particular point as well. This particular topic. What is that? That's dipole moment. My dear students, one thing which I believe you must are familiar with. If you have got two equal and opposite charges, if you have two equal and opposite charges, plus q and minus q, two equal and opposite charges separated by certain distance. Whenever you have got two equal and opposite charges separated by certain distance, the system of equal and opposite charges separated by certain distance, what do you call this as? You call this system as dipole. You call this system as dipole, right? You know it already. And for the dipole, what do we define? For the dipole, we define its moment, which is called as dipole moment. For the dipole, we define its moment, which is called as dipole moment, right? Which is represented by mu. And dipole moment is defined as the product of charge multiplied by the distance. And this dipole moment mu, it's a vector quantity. It is a vector quantity. If it is a vector quantity, that means it will have direction as well. It will have direction as well. And its direction in chemistry, is taken from positive to negative. Or you can say it is from less electronegative element to more electronegative element. Okay? It's from less electronegative element to more electronegative element. Let me tell you at the same time, the SI unit of dipole moment is d by. It is d by. Have a look now what I'll be saying. Let's say I'm taking a molecule HCl. Okay. Now among hydrogen, chlorine, which one is more electronegative? You know it. Chlorine is more electronegative. If chlorine is more electronegative, it will attract the bonded pair towards itself. So it will carry delta negative. This will carry delta positive. So can I say I have got equal and opposite charges separated by a certain distance? So can I say this particular molecule is behaving like a dipole? Right? It's behaving like a dipole. If it is behaving like a dipole, right? If it is behaving like a dipole, its moment will be from positive to negative. So this particular molecule has got dipole moment in this direction. Okay? It has got dipole moment in this particular direction. My dear students, that particular molecule whose net dipole moment will be zero. That particular molecule whose net dipole moment will be zero. You call that particular molecule as non-polar. And that particular molecule whose net dipole moment is non-zero, you call that molecule as the polar molecule. You call that particular molecule as the polar molecule. Remember these 2 points as well. Sometimes the question is asked, which of the following is a polar molecule? Which of the following is non-polar? You have to confirm the net dipole moment. Okay, you have to check the net dipole moment. If the net dipole moment comes out to be non-zero, it's polar. If the net dipole moment comes out to be zero, it is non-polar. Okay, so if I ask you, what about this HCl? Is this HCl? Is this HCl polar or non-polar? It has got some dipole moment. So it's a non-polar, it's a polar molecule. This particular one, it's a polar molecule. It is a polar molecule, right? Now, my dear students, one more thing I would want to add over here. That will ease out a lot of things for you. Okay? When you have to check whether the molecule is polar or non-polar, you have to check basically. What to check? Just check one thing. Just check whether the molecule belongs to the category AB2L0, or check if the molecule belongs to the category AB3L0. And how to check to which category molecule belongs to, I'll show that in some time. First of all, you remember it now. The molecule of the type AB2L0, the molecule of the type AB3L0, molecule of the type AB4L0, molecule of the type AB5L0, molecule of the type AB6L0, okay, molecule of the type AB7L0, molecule of the type AB2L3, AB2L3, molecule of the type AB4L2, AB4L2, all these molecules, whatever types I've mentioned over here, all these molecules, they are going to be what? They are going to be non-polar. They are always going to be what? They are going to be non-polar molecules. Remember this particular point as well, because this is important. Okay, because this is important. At the same time, people, one more important thing. Remember that the lone pair also contributes. Lone pair also contributes towards what? Lone pair also contributes towards the dipole moment. Lone pair also contributes towards the dipole moment. And remember, direction of moment due to lone pair is towards the lone pair. For example, this is the atom A. Let's say this is the atom A. Let's say it has got a lone pair here. Lone pair is also going to contribute. And the direction of the moment due to lone pair is towards the lone pair. I believe I'm clear to everyone. And if this is clear, we are good to go. We are good to go to solve certain questions. Or before solving certain questions, one more thing I would want to add here. What is that? See, as I told you, my dear students, your dipole moment, it is the product of charge and distance. Dipole moment is the product of charge and distance. That's something which I have told you. Perfect. In most of the cases, my dear students, remember, in molecules, more the electronegativity difference between the atoms. In a molecule, more the electronegativity difference between the atoms, more is going to be the dipole moment. Right? In majority of the molecules. So, whenever we have to compare dipole moments, the first thing which we'll be doing always, not always, there are some exceptions as well, which I'll show you. Okay? But majority of the times, we check the electronegativity difference between the atoms. And more the electronegativity difference, more is going to be the dipole moment. Okay? Now let's have a look. My dear students, you have got NH3, you have got NF3. Tell me which one has got more dipole moment. Quickly, what do you think? Quickly, everyone in the chats. NH3 or NF3, which one has got more dipole moment? Which one has got more dipole moment, people? Everyone. Absolutely. You all are perfectly right. It is NH3 which has got more dipole moment. Correct? As you can see one thing, why is it so? If you talk about your NH3, nitrogen has got a lone pair. If you talk about this NF3, this is the structure of your NF3. Now look carefully what I'll be saying. Among nitrogen and hydrogen is less electronegative. This is more electronegative. So moment is from less electronegative to more electronegative. Less to more. Okay? And here, due to the lone pair, it is towards the lone pair. So all the moments are converging in one direction. If we look here, due to the lone pair in this direction, less electronegative to more electronegative, less electronegative to more electronegative, less to more. Do you see some kind of cancellation here happening? So I would say this molecule has got more net dipole moment, okay? And this molecule has got comparatively less net dipole moment. I hope I'm clear. So remember, when it comes to NH3 and NF3, among NH3 and NF3, it's NH3 that has got more net dipole moment. I hope I'm clear to everyone. Now, look at this particular molecule. Carbon chlorine, less electronegative to more, less to more, less to more, less to more. See, equal and opposite moments, so cancel out. Perfect. Here, both are converging in one direction, two vectors in same direction. So I would say this will have more resultant, right? Perfect. HF, HCl, HBr, HI. Where is the electronegativity difference more? Here you find more electronegativity difference. And more the electronegativity difference, more is eventually going to be the dipole moment, right? So this is the order. I hope I'm clear to everyone. Now people, remember this particular one. You might do a mistake here. See, first of all, you have got, here is a bond between carbon fluorine. Here is the bond between carbon chlorine. As I told you, dipole moment, it is a product of two things, charge and distance, right? See, when it comes to the charge factor, as per charge factor, dipole moment of 1 would be greater than that of dipole moment of 2, because the electronegativity difference here is more. Since the electronegativity difference here is more, due to which charge on the atoms will be more. If charge will be more, dipole moment is more. Correct? This is as per charge. But as per distance factor, CCl bond length is more than that of CF. If CCl bond length is more than that of CF bond length, then as per distance factor, the dipole moment of second one has to be more than that of first one. Okay, so both are contradicting. And in this special case, distance dominates over everything. So remember this particular case, this CH3Cl has got maximum dipole moment, followed by CH3F, followed by CH3Br, followed by CH3I. Remember it in the form of a special case. Am I clear? My dear students? Quick, everyone. Right? Look at the next one. H2O, H2S. Bond is between oxygen and hydrogen. Bond is between sulfur and hydrogen. More electronegativity difference, more the dipole moment. Done. NH3, PH3. More the electronegativity difference, more the dipole moment. H2O, NH3. Bond is between OH. Bond is between NH. OH, more electronegativity difference. That means more dipole moment. Yeah? Am I clear, people? Am I clear to everyone? Quick in the chats. Everybody. Everybody, people. Okay? Let me know once in the chats with the fire emojis. Quick, people. Quickly. I believe I am clear to every one of you. Look at these examples as well. If you look at these examples, my dear students, you should know that CH3 is CH3 electron withdrawing or donating? What is CH3? Electron withdrawing or donating? CH3 is electron donating, right? This CH3 electron donates. It donates. If it donates electrons, this gets positive, this gets negative. This gets positive, this gets negative. Moment from positive to negative. Both the vectors are equal but opposite in direction. So its net dipole moment here is going to be 0. Okay? As simple as that. CH3 donating. So positive, negative. The moment is from positive to negative. Here it's also from positive to negative. If you look carefully, one vector is pointing downwards. One vector is pointing downwards and one vector is pointing in this direction. So they are right now at an angle of 120. Okay, these two vectors are right now at an angle of 120. See, again this is positive to negative, again this is positive to negative. One is pointing downwards, one is pointing in this direction at an angle of 60. Now tell me one thing. You have got two vectors here, right? At an angle of 120. Two vectors here at an angle of 60. You know, lesser the angle between the vectors, more is going to be the resultant. Lesser the angle between the vectors, more is going to be the resultant. So my dear students, resultant here is going to be more, right? So net dipole moment in the third case is going to be maximum, followed by second, followed by first. I believe this is clear. And if this is clear, look at the next example as well. This is donating. It donates electrons. So positive, negative. NO2 is withdrawing. It withdraws electrons. So negative and positive. So in this particular direction. So in this particular direction. One going downwards like this. One going in this particular direction. The angle here is 120. Positive, negative. NO2. It withdraws electrons. Negative, positive. In this particular direction. In this particular direction. So one vector going in this direction, one vector going in this direction at an angle of 60, right? Similarly, this direction, both the vectors going in the same direction. So angle here is 180, angle here is 180. So where do you see the resultant maximum? Where do you tell me, where do you see the resultant maximum? I'm asking you this question. Where is the resultant maximum? First, second or third? You can see in the third case, the resultant is maximum because both the vectors are going in the same direction, right? So the resultant is maximum in the last one. So net dipole moment in the third case is more than that of 2, than that of 1. Am I super clear to everyone? Will you be in a position to solve each and every question when it comes to your dipole moment? Yeah? When it comes to your dipole moment, will you be able to solve each and every question when it comes to your dipole moment? Quickly in the chats. I hope this is clear to everyone, yeah? Perfect, perfect. Oh, sorry, I mentioned 180. It's not 180, it's 0, sorry. They are going in the same direction. This is 0 degree. Yeah. Cool? I'm going slow only. Guys, am I going very fast? Am I going fast? Say yes or no. Because someone said you are going fast. Is it? Am I going fast? Everyone. Everyone. I know I'm not going fast. Yeah. I know I'm not going fast. I'm going slow only. And it's a normal pace. It's a normal pace. Okay, one more thing I would want to ask before continuing. How many of you solved the DPP of the last marathon which I shared on my Telegram? The ones who solved, say yes in the chats. The ones who did not, say no in the chats. And I would want the honest answers. I would want the honest answers. Yes, the physical chemistry one. The physical chemistry one. Okay, try to solve all of them, by the way. Huh? Try to solve all of them. Then only these marathons are going to be effective. Okay, then only these marathons are going to be effective. Please take care of this. Take care of this, huh? Dinner break will be given exactly at 9:30. So at 9:30, I'll be giving you the dinner break. Okay, so let's continue till 9:30. Now, my dear students, there is one more very important theory of this particular chapter. What is that? That is your valence bond theory. What this valence bond theory is going to teach us, what this valence bond theory is all about, let's have a look. My dear students, As per your valence bond theory is concerned, a covalent bond is formed by the overlap of atomic orbitals. A covalent bond is formed by the overlap of atomic orbitals of what? Of bonding atoms. As per your valence bond theory is concerned, a covalent bond between two atoms, it is formed when the atomic orbitals of the bonding atoms, when they overlap. What is meant by the overlapping? Overlapping of atomic orbitals means merging of atomic orbitals into each other. Merging of atomic orbitals into each other is something which you call as overlapping. So whenever you have got two bonding atoms, those atoms which have to form covalent bond, okay? First of all, in order to show the overlap, they should come closer. Right? They should come closer. And when they'll be coming closer, their atomic orbitals will be merging into each other. That merging of electron clouds, that merging of atomic orbitals into each other is something which you call as overlapping. And due to the overlapping, which bond gets formed? It is the covalent bond which gets formed due to the overlapping. Okay? So first of all, remember, a covalent bond is formed by the overlap of atomic orbitals into each other. And in order to show the overlap, the bonding atoms, they must come close. The bonding atoms must come close so that their atomic orbitals can overlap. Right? Now, my dear students, this is something which I told you already. What is overlapping? Imagine this is the atomic orbital of one atom. This is the atomic orbital of one more atom. Perfect? Right? In order to form a covalent bond, they should first of all come closer. When they will be coming closer, there will be a scenario when their atomic orbitals will penetrate into each other. And this penetration of atomic orbitals into each other is something which you call as overlapping. And due to overlapping, which bond gets formed? Covalent bond gets formed. As simple as that. As simple as that. Now, my dear students, this overlapping is exactly of two types. One is called as axial overlapping. One is called as parallel overlapping. This is something which we have to discuss in detail. What is axial overlapping? Whenever atomic orbitals penetrate into each other along the axes. So overlapping along the axes. Overlapping along the axes is what you call as axial overlapping. Overlapping along the axes, or you can call it directly as the head-on overlapping. You can call it directly as the head-on overlap. Okay? And due to this axial overlap, which covalent bond gets formed? It is always the sigma covalent bond that gets formed due to the axial overlap. Now, in case of parallel overlap, my dear students, in case of parallel overlap means overlapping by keeping, I'll show this in detailed format in some time, by keeping the axes parallel. Just remember it for now. You'll get the idea in some time. And due to this parallel overlapping, which bond gets formed? Either pi bond gets formed, or you can say delta bond gets formed. Pi bond formation takes place, or the delta bond formation takes place. Okay? Pi bond formation or the delta bond formation takes place. Right? Let's try to have a look on this axial parallel overlapping in detail. Have a look, guys. First of all, let's have a look on the axial overlapping. What happens in axial overlap? The atomic orbitals, they overlap along the axes. The first type of overlap here is SS overlap. SS overlap. Try to understand what I'll be saying. My dear students, first of all, imagine this is the internuclear axis. And generally internuclear axis is kept as Z-axis. Right? Let's say this is the s orbital of one atom and this is the s orbital of one more bonding atom. Okay? Let's imagine that. Now, for example, they are coming closer. When they are coming closer, there'll be a scenario when the atomic orbitals of these bonding atoms, they'll merge into each other. First of all, do you see it as the head-on overlapping? Yes, it's a head-on overlapping, right? What has happened? Penetration of atomic orbitals into each other. What do you call this as? You call this as overlap. Due to overlap, what happens? Covalent bond gets formed. And since it's a head-on overlap, so which covalent bond gets formed? It is a sigma bond. It is a sigma covalent bond that's going to get formed. And my dear students, what happens at the end? What happens at the end? This electron density, it comes under the influence of both the nuclei. This electron density, it comes under the influence of both the nuclei. It comes under the influence of both the nuclei. It comes under the influence of both the nuclei at the end. So this is what you call as SS overlapping. This is what you call as SS overlapping. My dear students, the second type of axial overlapping is your SP overlap. SP overlap. This is the second type of axial overlap. This is the second type of axial overlap. Have a look what exactly this SP overlap is all about. Let's say this is your internuclear axis. Or let me use one more slide. See, the second type of axial overlap is basically your SP overlap. SP overlap. Okay, SP overlap. I'm right now teaching you the axial overlap. Okay, let's say this is your internuclear axis, which is your Z axis. Let's say this is the S orbital of one atom, bonding atom, and this is the P orbital of one more bonding atom. Perfect. Two scenarios I'm going to show here. This is the S orbital of one atom. This is the P orbital of one more atom. Perfect. Now, my dear students, first of all, let me give certain signs here. Let me give this a positive sign. Let me give this positive. Let me give this negative. Okay. Right. Let me keep this positive. Let me keep this negative. Let me keep this positive. Well, these are not charges. I'm giving these signs basically. Right. Just remember it like this. Now, my dear students, first of all, this overlap is going to be head-on overlap. Perfect. Do you see same sign on same side? Yes, same sign on same side. Same sign, same side means positive overlap. Same sign, same side means positive overlap. Opposite sign, same side. Opposite sign, same side means negative overlap. Means negative overlap. Okay. Due to which bond formation does not take place. Bond formation takes place in the positive overlap. So what happens basically, these atomic orbitals, they are going to merge into each other. How exactly? This is your S orbital. This is your S orbital. This was your S. Now this P has penetrated into it. Perfect. And due to which overlapping has happened. Which overlapping? This is head-on overlapping. Due to which bond has got formed? I would say sigma bond has got formed. So this was your SP axial overlap. This was your SP axial overlap. The third one is your PP axial overlap. The third one is your PP axial overlap. PP axial overlap. And how this PP axial overlap looks like? Have a look. Let's say this is your internuclear axis. Okay. And since I'm going to show you two scenarios. So this is your internuclear axis. That is, for example, your Z axis. This is again your Z axis. So you have to show PP overlap. Let's say this is one of the P orbitals of one bonding atom, one more P orbitals of one more bonding atom. Similarly, one P orbital of one bonding, another P orbital of one more bonding. Now, first of all, let's give some signs. Positive, negative, positive, negative, positive, negative, negative, positive. What do you see? Same sign, same side. Same sign, same side. Same sign, same side is what you call as positive overlap. So is this head-on overlap? Yes. So I would say these atomic orbitals will merge into each other. These atomic orbitals, they will merge into each other. Yes, they have merged into each other. Right? Right, people? They have merged into each other. Now, this head-on overlap, which will lead to the formation of which bond? It is again going to be the sigma bond. Is the same sign on same side or opposite? I'll say it's opposite sign on same side. Opposite same sign, same side means negative overlap. And negative overlap does not lead to the formation of bond. Perfect. So I hope this axial overlapping is clear. And due to axial overlapping, sigma bond forms. Due to axial overlapping, sigma bond gets formed. Right? Now, my dear students, let's talk about parallel overlapping. Let's talk about parallel overlapping. Let's talk about parallel overlap. Let's talk about the parallel overlap. Let's talk about the parallel overlap. Okay. So people, the first type of parallel overlap which I'm going to show you over here, that is PP parallel overlap. PP parallel overlap. How it exactly happens? Let's say this is one of the p orbital. This is one more p orbital. Am I keeping their x's parallel? Yes, I'm keeping their x's parallel. I'm keeping their x's parallel. Let's say they are going to come close like this. Okay. So there'll be a scenario when their lobes will merge into each other like this. When their lobes will merge into each other like this. As a result of which, the final shape of the orbital, how it looks like, the electron density will be above. The electron density will be above and it will be below the plane like this. The electron density is above the plane and below the plane. Which plane am I talking about? Let me show that plane to you. The electron density is above this plane and below this plane. On this plane, there is no electron density. On this plane, there is no electron density, right? So this plane I'm calling as the nodal plane. I'm calling this as the nodal plane, right? At the same time, guys, which overlap this was? This was the parallel overlap, and parallel overlap leads to the formation of which bond? It leads to the formation of pi bond. It leads to the formation of pi bond. Okay, this was your PP parallel overlap. Similarly, if I talk about the second one, that is PD parallel overlap. That is PD parallel overlap. In case of your PD parallel overlapping, what happens? Let's say this is your p orbital. Okay, let's say this is your p orbital, and let's say this is your, for example, d orbital. Okay, by keeping their x's parallel, let them overlap. Okay, so this is what you call as PD parallel overlap. PD parallel overlap, due to which bond gets formed? Pi bond. And what do you call this particular pi bond as? You call this as p pi d pi bond. You call this as p pi d pi bond. Perfect. This particular pi bond is called as p pi bond. You call this particular bond as p pi bond. Right? There is one more which I would want to show. What is that? That is DD parallel overlap. That is DD parallel overlap. DD parallel overlap. Okay. Let's say this is one of your d orbital. And this is one more d orbital. Let them come close. So what happens? What happens? Their atomic orbitals, they are going to merge into each other like this, right? Since it's again the parallel overlap, due to which bond gets formed? Pi bond gets formed. And this particular interaction is also called as two-lobe interaction. This is called as two-lobe interaction. I hope I'm clear to everyone. If I'm clear, let me know once in the chats quickly. If I'm clear, let me know once in the chats quick. If I'm clear, let me know once in the chats quick. Everybody. Everybody, people. Okay. I'm not going to show you the delta bond here because that's not in your syllabus. Okay. Only sigma and pi bond is in your syllabus. And my dear students, remember few things. Remember few things about the sigma and pi. Remember, sigma bond is formed first, followed by a pi bond. Sigma bond is formed first, followed by the pi bond. Point number one. Point number two. Sigma bond is stronger than what? Than your pi bond. Sigma bond is stronger than your pi bond. Let's take one example so that you can understand the formation of a molecule as per VBT. For example, let's see how O2 molecule formation takes place. Let's see how O2 molecule formation takes place as per valence bond theory. As per valence bond theory. Try to understand, my dear students, what I'll be saying. See, this is one oxygen atom. This is one more oxygen atom. Okay. What is the outermost configuration of oxygen? Oxygen has got 2p4 configuration. This oxygen also has got 2p4 configuration. 2p4 configuration means 1, 2, 3, and 4. This is also your 2p4. 1, 2, 3, and 4. Let's call this as, for example, pz. Let's call this as py. Let's call this as px. Similarly, let me call this as pz. Let me call this as py. Let me call this as px. Okay. So first of all, if you talk about this particular oxygen, you have got 3p orbitals here. This is, for example, your pz. This is pz containing 1 electron. pz containing 1 electron. This is, for example, your py containing 1 electron. And similarly, let's say this is your px containing how many electrons? Containing 2 electrons, right? Now, on this side, oxygen is going to come. One of the pz of oxygen will come from this side and will do the head-on overlap. Okay, so sigma bond got formed here. At the same time, you have got py containing 1 electron as well. This is py containing 1 electron. Do you see this py and this py, they are parallel to each other? If they are parallel, they'll do the parallel overlap, which will lead to the formation of pi bond. At the same time, there is one more, that is px here. This is your px, it already contains 2 electrons, right? So do you see, over here sigma bond got formed, and over here which bond got formed? Pi bond got formed. So how do you make the structure finally? This is O, oxygen, first single bond, then double bond, like this, right? Am I clear, people, to everyone? Am I clear to everyone? Let me know once the chat's quick. Am I clear to everyone? Let me know quick in the chats, everybody. I want to have fire in the chats first. I want to have fire in the chats quick, everybody. Yeah? My next marathon is going to be class 11th physical chemistry. Don't worry. My next marathon is going to be class 11th physical chemistry. Okay? Perfect. So whatever things were required here, I've discussed all the things. Our next topic is hybridization. Do you want to start hybridization right now, or do you want to take the dinner break first? Because it will take time. It is 9:05. So let me give you a break first of all. Go for the dinner quick. I'll also have some tea or something. But I would want every one of you to be back on time. Huh? I would want every one of you to be back on time. Have your dinner. Okay? But I would request every one of you to be back on time. Otherwise, if everyone is not back on time, then it's better to cancel the session afterwards. Yeah? And one thing I'm telling you, this session is not going to be for 12, 13 hours. No. This session will maximum run for some 6 hours. Because we have got only lesser things to discuss here. It's not like the syllabus is not very huge when it comes to class 11th inorganic. In like 6 hours we'll be continuing, we'll be completing it. All right? So I'll see you exactly after the break, and I would want every one of you to be back on time. Okay? Everyone means everyone. Got it? Chalo guys, I'll see you then. I'll see you in a while. What's up, my dear kiddos? Where did I keep a marker? Just a second, guys. Just a second. So, is everyone back? Is everyone back? Quick, quick, quick in the chats, people. Let me know quickly in the chats. No, I did not eat anything. I just had some coffee. I just had some coffee. Because if I eat, then the marathon will be over. Are you guys done with your dinner? Are you guys done with your dinner? Are you guys done? Okay. All right. So, guys, just tell me one thing. Whatever things I discussed till now, is every single thing clear? Honestly, say yes or no. Honestly, I just want to know. Honestly, I just want to know. Whatever things I discussed till now, is every single thing absolutely clear? Just tell me that. Just tell me that. Yeah? Okay. Got it. So now in chemical bonding, there are how many topics left? Hybridization, VSEPR, bond angle, and MOT. Okay. So should we start? Should we start again? Perfect. Today your class 11th in organic chemistry will be done. Okay? Your class 11th in organic chemistry will be over today. I mean in this particular session. Perfect. So let's get going again and let's start the session. So my dear students, now we are going to enter into one more important part of the chapter, which is very, very, very important, I must say. So have the proper concentration of what I'll be doing. Okay, have a proper eye on your screen now. Perfect. So the topic is going to be your hybridization. It is going to be the hybridization. It is going to be the hybridization. So let me first of all tell you, there is a method of calculating the hybridization. There's a method of calculating the hybridization. What is that method called? That method is called as steric. That method is called as steric number method. Steric number method. Okay, there's a method by means of which we check the hybridization, and that method is what you call as the steric number method. So try to understand what do I do here? Try to understand few things. My dear students, I'm defining steric number as, steric number is basically sigma plus lone pairs. The number of sigma bonds that the central atom forms, the number of sigma bonds that the central atom forms, plus the number of lone pairs which are there on the central atom. Steric number is nothing but the number of sigma bonds that the central atom forms plus the number of lone pairs which are there on the central atom. Now, first of all, remember certain things, and after 5 to 10 minutes, you will understand each and every single thing in detail. Okay? Have a look, people. First thing which I would want you guys to remember. My dear students, if the value of steric number comes out to be 2, then hybridization of the central atom is going to be sp. The central atom is going to be sp hybridized. Okay? And the geometry which is predicted through hybridization, that is going to be linear. The geometry which is predicted through hybridization, that is going to be linear. Point number 1. Point number 2. If the steric number comes out to be 3, hybridization involved is going to be sp2. And geometry which is predicted through hybridization, that's going to be trigonal planar. That's going to be trigonal planar, right? Similarly, if the steric number comes out to be 4, hybridization involved is going to be sp3, and geometry predicted through hybridization is going to be tetrahedral. It's going to be tetrahedral. In the similar way, my dear students, if the steric number comes out to be 5, the hybridization involved is going to be sp3d, and the geometry which is predicted through hybridization, that's what you call as trigonal bipyramidal. Trigonal bipyramidal. And let me tell you, if the steric number comes out to be 6, hybridization involved is going to be sp3d2, and the geometry which is predicted through hybridization, that's going to be octahedral. That's going to be octahedral. And again, my dear students, remember, if the steric number comes out to be 7, the hybridization involved is going to be sp3d3, and the geometry which is predicted through hybridization, that is pentagonal bipyramidal. That is pentagonal bipyramidal. First of all, these are the things which I would want every one of you to remember. Point number 1. Okay. Point number 2. Take a note of it. When it comes to sp3 hybridization, which orbitals participate in sp3 hybridization? It is one of the s orbitals, one px orbital, one py, and one pz. These are the 4 orbitals which participate in the hybridization here. Similarly, when it comes to sp3d hybridization, sp3d, it's going to be s orbital plus 3 of the p orbitals, and apart from 3 p orbitals, it's going to be dz square, which participates in this hybridization. Similarly, in case of octahedral, in case of sp3d2, it's going to be s orbital, 3 p orbitals, px, py, pz, right? Similarly, it's going to be dx square minus y square, and at the same time, it's going to be dz square. And when it comes to your sp3d3 hybridization, it's going to be s, your px, py, pz, and it's going to be dxy, dz square, and dx square minus y square. These are, first of all, few points which are asked in your examination. Okay? Which d orbital is involved in sp3d? It's going to be dz square. Which d orbitals are involved in sp3d2? It's going to be dx square minus y square and dz square. Which d orbitals are involved in sp3d3? It's going to be dz square, dxy, and dx square minus y square. Now, my dear students, let's try to check the application of this particular part. That's very important. Have a look. For example, I'm taking the molecule as BeCl2. This is the molecule. Try to understand. This is very important now. Okay? BeCl2. Let's say this is the molecule. This beryllium over here is the central atom, first of all. If beryllium is the central atom, if I ask you, how many valence electrons beryllium has? Beryllium has 2 valence electrons. Hydrogen, helium, lithium, beryllium. Beryllium has got 2 valence electrons. Now, my dear students, how many surrounding atoms? How many surrounding atoms beryllium has? It has 2 surrounding atoms. Number of surrounding atoms is equal to number of sigma bonds. Remember this particular point. number of surrounding atoms is equal to the number of sigma bonds. Now, my dear students, since beryllium had 2 valence electrons and it is forming 2 sigma bonds, that means beryllium is utilizing both of its valence electrons. Beryllium is utilizing both of its valence electrons to form 2 sigma bonds. So that means there will be no lone pair on beryllium. There will be no lone pair on beryllium. If there is no lone pair on beryllium, I can calculate steric number. Steric number is going to be sigma plus lone pair. Sigma plus lone pair comes out to be 2. And if the steric number is 2, hybridization involved is going to be sp. And if hybridization involved is sp, that means geometry which is predicted through hybridization, that's going to be linear, right? So your BeCl2 is basically linear, right? I hope I'm clear to everyone. A simple and basic funda I'm teaching you right now, which is directly asked in your exam. No need to go in a lot of depth at this particular point of time. This is something which is asked. This is something which I'm teaching you, okay? Now, for example, let's say I've got BF3. Again, one simple molecule, BF3. Perfect. My dear students, the central atom over here is your boron. How many valence electrons boron has? How many valence electrons boron has? Hydrogen, helium, lithium, beryllium, boron. Atomic number 5. So 2, 3. So I would say boron has 3 valence electrons. How many surrounding atoms do you see here? 3 surrounding atoms. That means how many sigma bonds? 3 sigma bonds. Boron had 3 valence electrons. And it is utilizing all the 3 valence electrons to form 3 sigma bonds. So how many lone pairs are there on boron? 0 lone pairs. Okay. If I ask you to calculate the steric number, it's going to be sigma plus lone pair. That's 3. If the steric number is 3, hybridization involved is sp2. If the hybridization involved is sp2, the geometry predicted through hybridization is trigonal planar. Right? So how this BF3 finally looks like? This is B, F, F, and F. Okay? If you look carefully, the bond angle here is 180 degree. And here, it's going to be what? It's going to be 120 degree. I hope this is clear. Similarly, my dear students, for example, I'm taking one more simple molecule, that is CH4. That is CH4. Perfect. Now, my dear students, here the central atom is carbon. If the central atom is carbon, how many valence electrons carbon has? 4. Right? How many surrounding atoms are there? 4. That means sigma bonds are 4. That means sigma bonds are 4. Since carbon had 4 valence electrons, and it has utilized all the 4 valence electrons to form 4 sigma bonds. So, there will be no lone pair on carbon. Steric number is going to be 4 plus 0, 4. Hybridization is sp3. The geometry which is predicted through hybridization, that is tetrahedral. Right? That is tetrahedral. Carbon, hydrogen, 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 and hydrogen. And the bond angle here in this particular case is going to be 109 degree, 28 minutes. It's going to be 109 degree and 28 minutes. For example, let me take NH3. Let me take NH3. Perfect. Let me take NH3. If I first of all talk about the central atom, that is nitrogen, how many valence electrons nitrogen has? 5. How many surrounding atoms? 3. That means 3 sigma bonds. So nitrogen had 5 valence electrons. And it is out of 5, it is utilizing 3 of its valence electrons to form 3 sigma bonds. It is utilizing 3 of its valence electrons to form 3 sigma bonds. So I would say 2 electrons will be left as such on nitrogen in the form of a lone pair. So how many lone pairs on nitrogen? 1. If I ask you about the steric number, sigma plus lone pair, that's 4. If the steric number is 4, the hybridization involved is sp3. If I ask you what is the geometry predicted through hybridization, I'm not talking about the actual shape right here. I'm not talking about the actual shape right here. I'm talking about the geometry which is predicted through hybridization. That is tetrahedral. Okay. I hope I'm clear to all of you. So my dear students, like this, you calculate the hybridizations. Like this, you check the geometry which is predicted through hybridization. And in case of NH3, remember, the actual bond angle is 107 degree. Okay. Perfect. For example, you have got XCF2. Let's say you have got XCF2. Let's say you have got H2O. Okay. Let's say you have got NH4 positive. NH4 positive. Let's say you have got I3 negative. Let's check the hybridizations in these particular cases. Try to understand what do I do, my dear students. The central atom here is xenon. How many valence electrons xenon has? 8. How many sigma bonds it's forming? 2. Out of 8 valence electrons, 2 are being exhausted. So there are 6 valence electrons as such on xenon. in the form of 3 lone pairs. So there are 2 sigma bonds, 3 lone pairs. If I ask you about the steric number is sigma plus lone pairs, that's 5. If the steric number is 5, the hybridization involved is sp3d. As simple as that. Right? Similarly, talk about water. The central atom here is oxygen. How many valence electrons oxygen has? 6. How many surrounding atoms? 2. So sigma bonds are 2. So out of 6 valence electrons, oxygen is utilizing 2 of its valence electrons. Right? So there are 4 electrons as such left on oxygen in the form of 2 lone pairs. Right? So 2 sigma bonds, 2 lone pairs. Steric number is 2 plus 2, 4. If the steric number is 4, hybridization involved is sp3. Got it? NH4 positive. How many valence electrons nitrogen has? 5. But there is positive charge. So subtract this positive charge. The value comes out to be 4. The value comes out to be 4. Now, my dear students, how many surrounding atoms do you see? There are 4 surrounding atoms. Nitrogen had 4 valence electrons and it is utilizing all the 4 electrons to form 4 sigma bonds. So there is no lone pair on nitrogen. If I talk about steric number, 4 plus 0 is 4. Hybridization involved is sp3. Done? Similarly, I3 negative, for example. You can write I3 negative like this, I2 negative. I3 negative can be written like this as well, I2 negative. Let this iodine be the central atom. Valence electrons, 7. There is a negative charge. 7 plus 1 makes it 8. There is a negative charge. 7 plus 1 makes it 8. Right? Now, my dear students, how many surrounding atoms? 2. So sigma bonds 2. Out of 8 valence electrons, 2 are utilized. So out of 8 valence electrons, 2 are utilized. So 6 are left as such in the form of how many lone pairs? 3 lone pairs. Sigma 2 lone pairs 3. So if I talk about the steric number, 3 plus 2, 5. If steric number is 5, the hybridization involved is going to be sp3d. So is the concept of hybridization clear to everyone? Can you check the hybridization of each and every molecule from now onwards? Quick in the chats, everybody. Quickly in the chats, everyone. Is it clear to everyone, people? Quick. Everyone in the chats. Is it super clear to everyone? I want everyone to say it in the chats. Quick. Okay. Perfect. Perfect, guys. Perfect, perfect, perfect. Perfect. Let's move on. Let's move on, my dear students. So you got to know how to check the hybridization. That was my point. Now comes your valence shell electron pair repulsion theory. VSEPR. Okay. Valence shell electron pair repulsion theory. It's again super important. It's again super important. Okay. So my dear students, try to understand every single thing properly. My dear students, one simple thing. This valence shell electron pair repulsion theory, it's going to give us the idea about the actual shape of the molecule. It is going to give us the idea about the actual shape of the molecule. And my dear students, let me tell you one more thing. For example, you have got NH3. Let's say this is your NH3. Okay. And nitrogen has got one lone pair as well. You must know. Okay. First of all, nitrogen has how many valence electrons in total? Nitrogen has got some 5 valence electrons in total. Out of 5, these are the valence electrons of nitrogen which are participating in bonding. Right? Which are participating in bonding. So I call these 3 electrons as the bonding electrons. I call these 3 electrons as the bonding electrons. This electron, these 2 electrons, they belong to the valence shell of nitrogen. They belong to the valence shell of nitrogen, but they do not participate in the bonding. So I call them as the non-bonding electrons. I call them as the non-bonding electrons. Okay? Non-bonding electrons. Let me tell you, bonding electrons plus non-bonding electrons. Bonding electrons plus non-bonding electrons are what you call as valence shell electrons basically. They are what you call as valence shell electrons. Bonding electrons as well as the non-bonding electrons. You call them as combinedly as the valence shell electrons. Now, as per VSEPR, the valence shell electron pairs, as per your VSEPR, I'll say molecule tries to acquire that shape. The molecule tries to acquire that shape where the repulsions between the valence shell electron pairs are minimized. And if the repulsions are minimized, you can say stability is maximized. So as per your valence shell electron pair repulsion theory is concerned, molecule tries to acquire that particular shape wherein the repulsions between the valence shell electron pairs are minimized. And once the repulsions are minimized, that means the stability is automatically maximized. Okay? One more thing, people. One more thing. Try to understand. One more thing. Remember, lone pair repulsions are considered to be maximum, followed by lone pair bond pair repulsions, followed by bond pair repulsions. This is the order of the repulsions. Between your valence shell electron pairs. Okay? Between your valence shell electron pairs. I hope this is super clear. Now, let's get into the details of this VSEPR. So, try to understand very properly what kind of information this VSEPR is going to give us. Okay? What kind of information this VSEPR is going to give us. My dear students, let me start with the first case. What is that? Few minutes back, we have discussed steric number 3. We have discussed steric number 3 few minutes back. What is steric number first of all? Steric number is sigma plus lone pairs. Sigma plus lone pairs is what you call a steric number. Okay? My dear students, in case of steric number 3, what is the geometry predicted through hybridization? Geometry predicted through hybridization is trigonal planar. Okay? Trigonal planar. In case of steric number 3, the geometry predicted through hybridization is trigonal planar. Now, when can the steric number come out to be 3? Steric number can come out to be 3 if the central atom is forming 3 sigma bonds and if it has 0 lone pairs. Okay? If it has 0 lone pairs. Right? Steric number can come out to be 3 if the central atom is forming 3 sigma bonds and it has got 0 lone pairs. So sigma plus lone pairs gives you the steric number. That's 3. So if the central atom is forming 3 sigma bonds and lone pairs are 0, what is going to be the type of the molecule? The type of the molecule will be written like this. A is the central atom, B 3 sigma bonds and 0 lone pair. This is the type of the molecule. My dear students, remember one thing. Whenever you have got a molecule in which central atom does not have any lone pair. Let's say you have got a molecule wherein central atom does not have any lone pair. In that particular case, whatever is the geometry of the molecule predicted through hybridization, that is going to be the actual shape of the molecule. The point is, whenever you have got such a molecule, wherein the central atom does not have any lone pair, in that particular case, the geometry which is predicted through hybridization, that's going to give you the actual shape of the molecule. So if you look at this particular case, there is no lone pair on the central atom. Okay? So what is the geometry predicted through hybridization? That's planar. Geometry predicted through hybridization is planar. Right? So what is going to be the actual shape of the molecule? Actual shape of the molecule is also going to be planar. It's going to be trigonal planar. Perfect. It's going to be trigonal planar. Right? And how you are going to show it? It's going to be shown like this. A, this is B, and this is B. And all these 4 atoms They are present on the same plane. All these 4 atoms, they are present on the same plane. Okay. What is the bond angle in this particular case? The bond angle over here is going to be 120 degree. Okay. The bond angle in this particular case is going to be 20 degree. Now, my dear students, is there any other possibility to have steric number 3? There is one more possibility. If the central atom is forming 2 sigma bonds and the central atom has 1 lone pair. If the central atom is forming 2 sigma bonds and has 1 lone pair, right? Steric number also will come out to be 3. Steric number again will come out to be 3, right? So in this particular case, what is the type of the molecule? The type of the molecule is going to be AB2L1. 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 What is the geometry which is predicted through hybridization? Geometry predicted through hybridization is trigonal planar. But what is going to be the actual shape? What is going to be the actual shape? What is going to be the actual shape? Just do one thing. Make this geometry again. Make this AB3 geometry again. Now, do one thing. Remove one of the bond pair and instead of that, put a lone pair. Perfect. Now, if you hide this lone pair, how it looks like? If you hide this lone pair, how it looks like? It looks bent, right? So, the actual shape of the molecule is bent shaped. It is bent shaped. Okay? If you hide this lone pair, it will be bent. So, actual shape of the molecule is bent. Perfect. So, this was our first case wherein I talked about those molecules wherein the central atom has got the steric number of 3. Okay? Now, my dear students, let's say you have got one more type of those molecules wherein the steric number of the central atom is 4. And when the steric number is equal to 4, the geometry which is predicted through hybridization, that is tetrahedral. You know it already. Okay, and hybridization involved is sp3. In this particular case, in all these cases, this case as well as this case, where the steric number is 3, what was the hybridization? Hybridization was sp2. Hybridization was sp2. Now look carefully. Look carefully. I'm talking about those molecules wherein the steric number of the central atom is equal to what? Is equal to 4. Now tell me all the cases wherein we can have the steric number 4. See, the first case is if there are 4 sigma bonds. If the central atom is forming 4 sigma bonds, 0 lone pair. This is the first case. Second case can be if central atom is forming 3 sigma bonds and the central atom has 1 lone pair. This one more case. One more case, if the central atom is forming 2 sigma bonds and the central atom has got 2 lone pairs. In all these 3 cases, 4 plus 0 is 4, 3 plus 1 is 4, 2 plus 2 is 4. In all these 3 cases, steric number is equal to 4. What is going to be the type of this particular molecule? The type of this molecule is going to be AB4L0. The type of this particular molecule is going to be AB3L1. The type of this particular molecule is going to be AB2L2. Right? You got the types of the molecules. Now, people, if you look carefully, this is the molecule wherein the central atom does not have any lone pair. That means whatever is the geometry predicted through hybridization, that is going to give you the actual shape of the molecule. That's going to give you the actual shape of the molecule, which is tetrahedral. Perfect. So how do you show it exactly? Let's say this is A, this is B, for example. This is one more B, and one more B. This is your tetrahedral structure wherein the bond angle is 109 degree, 28 minutes. I hope this is clear. If we look at this particular case, the second case, sigma 3 lone pair 1. Type of the molecule is AB3L1. Okay, AB3L1. Geometry predicted through hybridization is tetrahedral. But what about the actual shape? What about the actual shape of the molecule? Actual shape of the molecule is going to be trigonal pyramidal. Actual shape of the molecule is pyramidal. What you need to do exactly? Just make this geometry again, AB4 type. When you make this geometry again, AB4, do one thing. Remove one of the bond pair and put a lone pair here. Remove one of the bond pair, put a lone pair here. Okay? Remove one of the bond pair and put a lone pair here. Perfect. Now, my dear students, if you hide this lone pair, this molecule will look like pyramidal. This molecule will look like pyramidal. Yeah? This molecule will look like pyramidal. Okay? I hope this is clear. Now, AB2L2 type. AB2L2 type. Geometry, already you know, which is predicted through hybridization. What is that? That is tetrahedral. Now, what about the actual shape of the molecule? What about the actual shape of the molecule? Just make the geometry once again. Make the geometry once again. Tetrahedral geometry, make it. Now from this particular geometry, remove two bond pairs. Remove two bond pairs, and instead of these bond pairs, put two lone pairs. Okay, put two lone pairs. It is V-shaped. It is V-shaped. Okay, it is V-shaped. It is V-shaped. So these are the cases of those particular molecules. These are the cases of those particular molecules wherein we can have the steric number equal to 4, right? Now we are going to talk about those molecules wherein the central atom is going to show the steric number of 5. And when the steric number is 5, you must be knowing, when the steric number is 5, the hybridization involved is going to be sp3d, and geometry predicted through hybridization is going to be trigonal bipyramidal. It's going to be trigonal bipyramidal. You know it already. It's going to be trigonal bipyramidal. Now, people, one more thing. What all possibilities do we have? What all possibilities do we have to have the steric number 5? Let's talk about all those possibilities one by one. So the first possibility is if there are 5 sigma bonds and 0 lone pairs. First possibility. Second possibility, 4 sigma bonds, 1 lone pair. Right? Next possibility, 3 sigma bonds, 2 lone pairs. Next possibility, 2 sigma bonds, 3 lone pairs. In all these 4 cases, you will have, in all these 4 cases, what do you have? You have got the steric number 5. Okay. See, the first case, wherein the type of the molecule is AB5L0. What is the type of the molecule here? It is AB4L1. What is the type of the molecule here? It is AB3L2. What is the type of the molecule here? It is AB2L3. It is AB2L3. So first of all, you got to know about the types of the molecules. You got to know about the types of the molecules. Now, after getting to know the types of the molecules, see, this is the case wherein the central atom does not have lone pair. So whatever is the geometry predicted through hybridization, that is going to be the actual shape of the molecule. And the actual shape of the molecule is nothing but, it is going to be your trigonal bipyramidal. It is going to be trigonal bipyramidal. Okay, it's going to be trigonal bipyramidal. Right, my dear students? Now, how it looks like exactly, AB5L0. This is A, for example. This is B. This is one more B. This is one more B. Perfect. So imagine as if all these 4 atoms, they are present on the same plane. Imagine as if all these 4 atoms, they are present on the same plane, right? Now, there will be one B perpendicular above the plane, one B perpendicular down the plane, right? My dear students, you should know one thing here. This bond, and this bond, which are present on the same plane, what do you call these bonds as? This white colored bonds, they're called as equatorial bonds. They're called as equatorial bonds. And these yellow colored bonds, this one and this one, they're called as the axial bonds. They're called as the axial bonds, right? They're called as the axial bonds. At the same time, see, between this equatorial and equatorial, between this equatorial and this equatorial, what is the bond angle? Between equatorial and equatorial, the bond angle is 120 degree. Between equatorial, the bond angle is 120. At the same time, how many 120s do you see? 1, 2, and 3. There are 3 120s. There are 3 120s here, if you look carefully. If I ask you, what is going to be the bond angle between axial and equatorial? Axial and equatorial. See, these 3 bonds, they are present on the same plane. Perpendicular to them is the axial bond, right? So between axial and equatorial, the bond angle is how much? 90 degree. And how many 90 degrees do you see here? One with this, one with this, one with this. So 3 from the top and 3 from the bottom. There are 6 90 degrees which you can see here. There are 6 90 degrees which you can see here. In the similar way, my dear students, do you see any 180 degree bond here? See, between this axial and axial, between axial and axial, there is 180 degree bond. There is 180 degree bond angle here. Okay? I hope this is clear to everyone. I hope this is clear to everyone. So this was your AB5L0 type trigonal bipyramidal. Okay, now comes one more case. Now comes one more case. Try to understand this as well. The type of the molecule is AB4L1. Okay, the type of the molecule is AB4L1. Geometry predicted through hybridization is what? That is your trigonal bipyramidal. Geometry predicted through hybridization. What about the actual shape? Let me directly tell you, the actual shape here is going to be seesaw. This is called a seesaw shape. It's called a seesaw shape. Okay. Similarly, AB3L2 type. Geometry, you know, trigonal bipyramidal. What about the actual shape? Actual shape, AB3L2 type. It is going to be T-shaped. Its actual shape is going to be T-shaped. Similarly, AB2L3. Its actual shape is going to be linear. Its actual shape here is going to be what? It is going to be linear. I hope all these cases you guys are remembering with me. Am I clear? Am I loud and clear? Let me know once in the chats, my dear students. Am I clear to everyone? Quick. Am I clear to everyone? Quick. Yeah? Amazing. So these were the molecules wherein the central atom shows steric number 5. Now what is the next case? Next case is where the central atom shows steric number 6. Steric number 6 means hybridization involved is sp3d2, and geometry predicted through hybridization is going to be octahedral. It's going to be octahedral. Now, how many possibilities do we have in this particular case? Let's talk about all those possibilities one by one. The first possibility is sigma bonds are 6, lone pair is 0. Second possibility is sigma bonds 5, lone pair 1. Third possibility is sigma bonds 4 and lone pairs are 2. These are the three possibilities which we see in this particular case. Okay? These are the three possibilities which we see in this particular case. What is going to be the type of the first molecule? It's going to be AB6L0. What is going to be the type of the second molecule? It's AB5L1. What is going to be the type of this particular molecule? It's AB4L2. My dear students, remember them directly. See, in the first case, lone pairs are 0. If lone pairs are 0, that means geometry, which is predicted from hybridization, that's going to be the actual shape, which is nothing but octahedral. Which is nothing but octahedral, right? Which is nothing but octahedral. AB5L1 type. AB5L1 type is going to be, its actual shape is going to be square pyramidal. Its actual shape is going to be square pyramidal. And AB4L2 is going to be square planar. It is going to be square planar. Okay, remember them directly. They are directly asked. They are directly asked. I hope I'm clear. Now the last case, what is that? That is steric number 7. The last case, that is your steric number 7. And in case of steric number 7, you know the hybridization involved is sp3d3, right? Geometry predicted through hybridization is pentagonal bipyramidal. Pentagonal bipyramidal. Okay, it's pentagonal bipyramidal. Now, how many cases do we have here in this particular one? See, the first case is 7 sigma bonds, 0 lone pair. The second case is 6 sigma bonds, 1 lone pair. The type of the first molecule is AB7L0. The type of the second molecule is AB6L1. AB6L1. Right here in this particular case, wherein the central atom does not have any lone pair, whatever is the geometry predicted through hybridization, that is the actual shape. And what is that? That is simply pentagonal bipyramidal. That's simply your pentagonal bipyramidal. Okay. If you look at the next one, AB6L1 type. Okay. Its actual shape is going to be distorted octahedral. It is distorted octahedral. Perfect. This is the actual shape of the molecule. So my dear students, once you get to know the type of the molecule, after that, you can talk about anything. Okay? Am I clear? Am I clear to everyone? Am I clear to everyone? Am I clear to everyone quickly? Tell me the type of this molecule. 2 sigma bonds, 0 lone pairs. The type of this molecule is AB2L0. The type of this molecule is AB3L0. The type of this molecule is AB4L0. The type of this molecule is AB3L1. And if you got the types of these molecules, you can talk about their shape, the actual shape. You can talk about their actual shape, right? You can give their actual shapes. See, 2 sigma, 3 lone pairs. Steric number is 5. What is the type of the molecule? Type of the molecule will be AB2L3. What is the type of this particular one? It's AB2L2. The type of this particular one is AB4L0. The type of this particular one is AB2L3. Okay? And once you get to know about the type of the molecule, you are done. Am I clear to everyone? Am I clear to everyone? Let me know once in the chats, quickly. Am I clear to everyone? Let me know once in the chats. Quick. Guys, only things you just have to remember the shapes. That's it. That's asked when it comes to your VSEPR. That's what is asked from your VSEPR. Nothing else. Nothing else. Perfect? All clear till here? All clear till here? Is the VSEPR clear? Is the VSEPR clear? Can you solve any question from it? Can you tell me the actual shape of this molecule? Its type is AB2L3. AB2L3 means linear. AB2L3 means linear. Okay? AB2L3 means linear. Have I written linear only here? Yeah. All right. My dear students, one more important concept which is asked in your exam. Okay? That is questions based on bond angle. Questions based on bond angle. Now, in this particular topic, the questions which are based on bond angle, I'll give you one diagram. Okay? Just remember that diagram, and from that diagram only, you can get each and every question. From that diagram only, you can get each and every question. Now, what is that diagram? Let's have a look. Let's have a look. People, you're supposed to remember this first of all. You're supposed to remember this first of all. Try to understand how do we remember this. So first of all, whenever question is asked wherein you are given with few molecules and you are supposed to arrange them as the basis of, you are supposed to arrange them on the basis of their bond angle. Whenever you are given with certain molecules and you are supposed to arrange those molecules on the basis of their bond angles. The first and the most important thing, you'll be using VSEPR. First of all, you'll be using VSEPR. That means you'll be checking the type of the molecules. You'll be checking the type of the molecules. If the molecule is of the type AB2L0 or AB2L3, if the molecule is of the type AB2L0 or AB2L3, okay, the molecule is going to be linear and it will have the maximum bond angle of how much? 180 degree. So the first and the most important thing, in the beginning itself, whenever you are given with 2-3 molecules, okay, you have to compare their bond angles. The first thing, check VSEPR, check the type of the molecule. If there is any molecule of the type AB2L0 or AB2L3, that means the molecule is going to be linear. And if the molecule is linear, the bond angle is going to be 180. Point number one. Point number one. Point number two. If you are unable to decide as per VSEPR, I'll show you examples in some time. First of all, remember. If you are unable to decide as per VSEPR, then go for hybridization. Calculate, check the hybridization of the central atom in all the molecules. Okay? If the hybridization of the central atom is different, for example, in one molecule, hybridization is sp, another one sp2, sp3. You know, in sp, the bond angle is 180. Here the bond angle is 120. Here the bond angle is 109 degree 28 minutes. So the one wherein sp is involved, that will have the maximum bond angle. First of all, VSEPR. If you are unable to decide as per VSEPR, then go for what? Go for hybridization. If hybridization of the central atoms is different in all the molecules, sp1 will have maximum, followed by sp2, followed by sp3. Okay. If hybridization is not different, if hybridization is same, the molecules which are given to you, if the hybridization of the central atoms in all the molecules is same, then two cases arise here. First case, if lone pair is absent on the central atom, and if lone pair is present on the central atom. If lone pair is absent on the central atom, then you have to give your answer as per hybridization. Okay. If hybridization is same and also lone pair is absent on the central atom, then give your answer as per hybridization. What does that mean? You'll get the idea in some time. But before that, one more thing. If hybridization is same and there is lone pair present on the central atom, then remember, bond angle is inversely proportional to the number of lone pairs present on the central atom. Okay? Bond angle is inversely proportional to the number of lone pairs present on the central atom. And at the same time, if hybridization as well as the number of lone pairs on the central atom are same, then my dear students, remember, bond angle is directly proportional to the size of surrounding atom, and at the same time, bond angle is inversely proportional to the size of central atom. First of all, this is the diagram which you have to remember. Now, from this diagram, we can solve each and every question. How exactly? Have a look. I'll show you certain questions, and with that, we'll be done. First of all, among these three, we have to arrange them as per their bond angles. See how I'll be solving now. First of all, check the type of this molecule. If you check the type of this molecule, it's AB2L0 type. This is also what? This is also AB2L0 type. This is AB2L3 type, right? As I told you in the beginning itself, if you have got the molecule of the type AB2L0 or AB2L3, their bond angle is maximum how much? 180. So all these three, they will have equal bond angles, and how much? That's going to be 180 degree. Okay, that's going to be 180 degree. Perfect. I hope this is clear. Now go to the second one. See, the type of the molecule here is AB2L0. The type of the molecule is AB3L0. The type of the molecule is AB4L0. Perfect. AB4L0. So on the basis of type of the molecule, you cannot decide. Now go for the hybridization. Hybridization involved here is sp. Hybridization involved here is sp2. Hybridization involved here is sp3. So hybridization is different. And when hybridization is different, sp has got maximum bond angle, followed by sp2, followed by sp3. Done? Now, go to the next one. Hybridization involved here is sp3. Hybridization involved here is also sp3. Hybridization here is also sp3. So in all these three cases, hybridization is same. Central atom has got 0 lone pair. Here the central atom has got 1 lone pair. Here the central atom has got 2 lone pairs. So hybridization is same, and the central atom has got lone pair. Okay? Hybridization is same, but the central atom has got lone pair. Now how you guys are going to decide here? Hybridization is same, central atom has got a lone pair. Hybridization is same, central atom has got the lone pair. Okay? Bond angle is inversely proportional to number of lone pairs. So more the lone pairs, lesser the bond angle. So this is the order here. I hope I'm clear. Look at the next one. See, hybridization involved here is sp2. Here also it is sp2. Here also it is sp2. Right? In all these three cases, hybridization is same. And there is no lone pair on the central atom. Now, my dear students, I've told you, when hybridization is same and there is no lone pair on the central atom, give your answer as per your hybridization. Since hybridization is same, so they will have equal bond angles. Right? They'll have equal bond angles. I believe I'm clear with this. Talk about this one. AB4L0, AB4L0, AB4L0. No lone pair on the central atom. Hybridization is same. No lone pair on the central atom. Give your answer as per hybridization. Equal bond angles. Okay. Perfect. Hybridization again same. This is sp3, this is sp3, this is sp3. Hybridization same. Number of lone pairs on the central atom also same. Number of lone pairs on the central atom also same. Hybridization same. Number of lone pairs also same. If hybridization and number of lone pairs both are same, then bond angle is directly proportional to the size of surrounding atom. Bond angle is directly proportional to the size of surrounding atom. And bond angle is inversely proportional to the size of central atom. See, look at the central atom. These are the central atoms. Bond angle is inversely proportional to the size of central atom. Right? Lesser the size of central atom, more the bond angle. So this central atom has got minimum size, so more bond angle. So this is the order. This is the order. Okay. Look at the next one. Look at the next one. NF3, NCl3, NBr3. Perfect. First of all, in all these three cases, again, hybridization as well as the number of lone pairs are same. Hybridization as well as the number of lone pairs are same. So how do you decide now? Bond angle is directly proportional to size of surrounding atom. More the size of surrounding atom, bromine has got more size, so more bond angle. Okay. This I'm giving you as the homework. You can check it out afterwards. In the similar way. In the similar way. Am I clear till here, people? Quickly, let me know in the chats. Am I clear till here? Am I clear till here? I think I need to block certain people. I think I need to block certain people. Wait. Let me check who all are spamming. Someone is saying, और बताओ तुम्हारी hobbies. कल बताता हूँ, ठीक है? You're blocked. Number 1. Okay. There is one. Hey, do you want to talk with me? Wow. No, I don't want to talk to you. You're blocked. All right. Who else? Block Shreya and Ramcharan. Where is Shreya? Let me find Shreya. Yes, Shreya. Where are you? Not see you. Wait. Who else needs to be blocked? Tell me. Someone is asking what business your father does. Businessman. Blocked. Who else? Who else? Who else? Will there be an academy offline classes in Tamil Nadu? Already there are already like Unacademy centers in Chennai. Okay. In Chennai there is. In Hyderabad also there is the center, yeah. In Hyderabad also. Sir, I want to see you without beard. Yeah, I'll do the clean shave tomorrow. I'll send you a picture of mine. I'll do the clean shave tomorrow and send you the picture. Cool? Yeah? Perfect. Should we continue now? This is the last topic of chemical bonding, and you are done with chemical bonding with this particular one. कश्मीरी में क्या बोलूं मैं क्या वन बकशीर पट Even you cash the boson, he bosna bu. So guys, still here, whatever things I've discussed, is every single thing clear? Whatever things I discussed till now, is every single thing clear? Let me know quickly in the chats. And I'm asking everyone. Okay, I'll tell HSP sir to send you the PDF of the last session. All right. Let's move on then. Let's move on, guys. Let's move on. And let's talk about the molecular orbital theory. My dear students, from the molecular orbital theory, there are few types of the questions asked. Okay? There are few types of the questions asked. The first and the most important question which is asked almost every year, what is that? That is how to calculate bond order. Number one, how to calculate bond order. Number two, how to check whether the species is paramagnetic, diamagnetic. Number two. Number three, calculation of magnetic moment. Okay. Number four, questions based on bond dissociation energy. Questions based on bond dissociation energy. Questions based on bond length. Okay, questions based on bond length. So all these things we are going to get this molecular orbital theory. And I'm going to give you the crux of it, remember it, and all your questions you can get from this. Okay, let's have a look. First of all, this molecular orbital theory, it is the extension. This MOT, it is the extension of what? It is the extension of your valence bond theory. MOT, molecular orbital theory, it is the extension of your valence bond theory. My dear students, as per MOT is concerned, as per molecular orbital theory is concerned, atomic orbitals of the bonding atoms. Atomic orbitals of the bonding atoms. What do? They combine. They combine and form molecular orbitals. Atomic orbitals of the bonding atoms, they combine and form what? They form the molecular orbitals. Remember, number of atomic orbitals combined. Number of atomic orbitals combined is always equal to the number of molecular orbitals formed. Number of molecular orbitals formed. So first of all, let's say this is one of the atomic orbital of one bonding atom, and this is one more atomic orbital of one more bonding atom. They are going to combine. Since two atomic orbitals are combining, so two molecular orbitals will get formed. One molecular orbital is called as bonding molecular orbital. one is called as anti-bonding molecular orbital. Anti-bonding molecular orbital. Let me tell you, energy of the bonding molecular orbital is less and its stability is more. Energy of anti-bonding molecular orbital is more and stability is less. Okay, and stability is less. Perfect. Now guys, one thing. Let's say this is the s orbital of one bonding atom and this is one more s orbital of one more bonding atom. Now, as per your MOT is concerned, okay, these two atomic orbitals, they are going to combine. And since two atomic orbitals are combining, therefore two molecular orbitals will get formed. One is going to be bonding, one is going to be anti-bonding. Since it's going to be head-on, right? So, what do I get? Due to head-on, remember your VBT. Due to head-on overlap, sigma bond suits get formed. So one, since is called as bonding molecular orbital, one is called as anti-bonding molecular orbital, and bonding molecular orbital I'll be representing with sigma 1s, and anti-bonding here I'll be representing with sigma star 1s. Anti-bonding I'll be representing here with sigma star 1s. Okay. For example, this is one of the p orbitals of bonding atom. This is one more p orbitals of bonding atom, right? Let's say they are combining. They are combining and they will lead to the formation of two molecular orbitals. Now it's parallel basically, and through parallel, what happens? Pi bonds are formed. So over here you get first of all bonding molecular orbital as well as anti-bonding molecular orbital. And my dear students, this bonding molecular orbital, let's say this is your, for example, 2py. Let's say this also 2py. So this bonding molecular orbital is going to be pi 2py. And this anti-bonding molecular orbital is going to be pi star 2py. Pi star 2py. Okay. First of all, these are the things which you should know. So your atomic orbitals of the bonding atoms, they combine and they lead to the formation of molecular orbital like this. Okay. Out of which few are bonding and few are anti-bonding. Now, my dear students, once these molecular orbitals are generated, then we have to fill the electrons. In these molecular orbitals. Once these molecular orbitals are generated, then after that, we have to fill these molecular orbitals by the electrons. And we have to fill them as per your Abba's principle, as per your Pauli's exclusion principle, and as per your Hund's rule. Remember these points. Once the molecular orbitals are generated, after that, we have to fill electrons in these molecular orbitals as per your Abba's principle, Pauli's exclusion, as per your Abba's principle, Pauli's exclusion principle, as well as your Hund's rule. Okay. And once we fill electrons in these molecular orbitals, after that, we can easily calculate bond order. How exactly? Half of number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. I'll show you its application in some time. Just first of all, remember these things. Okay. First of all, the atomic orbitals of the bonding atoms, they are going to combine. They will lead to the formation of molecular orbitals. Once these molecular orbitals are generated, then we have to fill electrons in these molecular orbitals as per Abba's principle, Pauli's exclusion principle, and as per Hund's rule. Once you fill electrons in these molecular orbitals, then you can calculate bond order, which is half of number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. And my dear students, remember, if the bond order comes out to be 1, that means there's a single bond between two atoms. If the bond order comes out to be 2, that means there's a double bond between two atoms. If the bond order comes out to be 3, that means there's a triple bond between two atoms. Okay. If the bond order comes out to be less or equal to 0, that means the molecule does not exist. Molecule does not exist. The molecule is not viable. Okay, remember this particular thing as well. Now, I'm going to go into the actual part. What is that actual part? Have a look. My dear students, as I told you, once the molecular orbitals are generated, after that, we have to fill electrons in these molecular orbitals. And we have to fill the electrons in these molecular orbitals as per their increasing energy. And this is the increasing order of energy of these molecular orbitals. And this is the energy order which you guys are going to follow till 14 electrons. What does that mean? Have a look. Let's say this H2. In H2, how many electrons are there? In one hydrogen, 1 electron. 2 hydrogen means 2 electrons. So in total, there are 2 electrons, right? Every orbital can accommodate a maximum of 2 electrons. So these 2 electrons will go here. So its configuration becomes sigma 1s2. Okay, sigma 1s2. Perfect. This is the configuration of H2. Similarly, He2, there are 4 electrons. So 2 here, 2 here. So its configuration becomes sigma 1s2, sigma star 1s2. Sigma star 1s2. Let's say Li2, total 6 electrons, 2 here, and 2 here. So its configuration becomes sigma 1s2, sigma star 1s2, and sigma 2s2. Okay. Let's say Be2, total 8 electrons, 2, 4, 6, and 8. Right? So its configuration is going to be sigma 1s2, sigma star 1s2, sigma 2s2, and sigma star 2s2. Sigma star 2s2. Perfect. Right? Now people, try to understand. Try to understand. See, this is bonding, this is bonding, this is anti-bonding. Bonding, anti-bonding, bonding. Bonding, anti-bonding, bonding, anti-bonding. Right? Now calculate the bond order. That's it. Bond order is going to be half of electrons in bonding. So how many are in bonding? 2. How many are in anti-bonding? 0. So the bond order comes out to be 1. That means between 2 hydrogen atoms, there is a single bond. Okay. Talk about this one. Bond order is equal to half of electrons in bonding. How many? 2. Minus anti-bonding, 2 electrons. Right? So 2 minus 2 is 0. So bond order here comes out to be 0. That means He2 does not exist. He2 does not exist. Look at the next one. Bond order is going to be half of electrons in bonding. So 2 plus 2 makes it 4. Minus anti-bonding is 2. 4 minus 2 is 2. 2 by 2 is 1. So bond order is 1. That means between 2 lithium atoms, there is a single bond. Okay. Talk about your Be2. Calculate the bond order. Half of number of electrons in bonding. 2, 4. Minus number of electrons in anti-bonding. 2, 4. The value comes out to be 0. So this Be2 molecule, it also does not exist. At the same time, one more thing, if I check, is there any unpaired electron here? No. Is there any unpaired electron here? No. See, every orbital, every molecular orbital can accommodate a maximum of 2 electrons. So no unpaired electron here, no unpaired electron here, no unpaired electron here. If there is no unpaired electron, that means what? That means these species are going to be diamagnetic. There is no unpaired electron anywhere. All these molecular orbitals, they are carrying 2 electrons each. Okay? They are carrying 2 electrons each. So there is no unpaired electron. If there is no unpaired electron, what does that mean? What does that mean? That means these species are going to be diamagnetic. Okay? They are going to be diamagnetic. Let's have a look on few more things. Let's have a look on few more things. This is B2 molecule. So in total 10 electrons in B2. One boron has 5 electrons. 2 boron has got 10 electrons. So 2 here, 4, 6, 8. Okay. Now, the energy of these 2 molecular orbitals is same. They are degenerate. They are degenerate. As per Hund's rule, pairing does not happen. Pairing does not happen until each degenerate orbital gets 1 electron. This is degenerate, this is degenerate. So give this 1 electron, give this 1 electron. Okay. Now have a look. 2, 4, 6, 8, and 10. So if I calculate the bond order is going to be half of number of electrons in bonding. 2, 4, 5, 6. Minus anti-bonding. 2, 4. 6 minus 4 is 2. 2 by 2 is 1. So bond order here is 1. Do you see unpaired electrons here? Yes, there are 2 unpaired electrons. If there are 2 unpaired electrons, that means this B2 species is going to be paramagnetic. It's going to be paramagnetic. How do you calculate its magnetic moment? How do you calculate its magnetic moment? Under root of n into n plus 2 over magnetrons. N represents the number of unpaired electrons. So how many unpaired electrons? 2. So 2 multiplied by 2 plus 2. So 2 plus 2 is 4. 4 2s are 8. So root of 8 Bohr magnetrons is the magnetic moment of this particular species, that is B2. Okay. C2 molecule. In C2 molecule, there are in total 12 electrons. 1 carbon has got 6. So 2 carbon has got 12 electrons. So 2, 4, 6, 8, 9, 10, now 11, 12. Pairing has been done. Pairing has been done. If you calculate the bond order, half of number of electrons in bonding, 2, 4, 6, 8. Minus number of electrons in anti-bonding, 2, 4. 8 minus 4 is 4. 4 by 2 is 2. So bond order is 2. So in case of C2 molecule, there is a double bond. But remember, this is a special case. In case of C2 molecule, both these bonds are pi bonds. Both these bonds are pi bonds. In case of C2 molecule, remember this directly. Okay? In case of C2 molecule, both these bonds are pi bonds. Now, do you see any unpaired electron here? No, there is no unpaired electron. So this particular species, C2, is diamagnetic in nature. Okay? For example, I've got N2. I've got N2. You can check it like this. N2, then N2 positive, then N2 negative. You can check it like this. Okay? You can check it like this. Perfect. You can check it like this. I hope this is clear. My dear students, I'm giving you one direct trick. Remember that trick also. Whenever you see a 14 electron species, its bond order is always going to be 3. Okay? Whenever you see a 15 electron species, its bond order is going to be 2.5. Whenever you see a 16 electron species, its bond order is going to be 2. So reduce 0.5, 0.5. Whenever you see 17 electron species, its bond order is 1.5. Whenever you see 18 electron species, its bond order is 1. Whenever you see 13 electron species, its bond order is 2.5. Reduce again. Whenever you see 12 electron species, its bond order is 2. Whenever you see 11 electron species, its bond order is 1.5. Whenever you see 10 electron species, its bond order is 1. Remember this. Okay? Remember this. And at the same time, bond order means number of bonds between two atoms, right? Is inversely proportional to bond length. More the bond order, more the bonds, closer the atoms, lesser the bond length. Okay? Bond order is directly proportional to bond dissociation energy, or you can say bond order is directly proportional to I'll say directly the stability. So anything can be asked from here. For example, I've got N2 molecule. Okay, I've got N2 positive. I've got, for example, N2 negative. Understand? See, first of all, give the order of their bond order. See, N2, one nitrogen has got 7 electrons, 2 has got 14. So it is a 14 electron species. Take 1 electron out, this is a 13 electron species. This is a 15 electron species. Right? So bond order of N2 is going to be 3 because it's a 14 electron species. It's 3. N2 positive, 13 electron species, 2.5. N2 negative, 15 electron species, 2.5. So bond order is going to be N2 will have maximum bond order, N2 positive and N2 negative. They have same bond order, 2.5. Okay. Now, my dear students, if I need to talk about the stability, bond order is directly proportional to stability, right? So more stable is going to be definitely N2 because it has got more bond order. Now, among N2 positive and N2 negative, remember one simple thing. If you have got two species which have got same bond order, remember that species which has got more antibonding electrons than that of bonding electrons. That species which has got more antibonding electrons than bonding electrons, its stability is going to be less. N2 positive, N2 negative. No doubt their bond order is same, but N2 positive has got lesser antibonding electrons. And lesser the antibonding electrons, more the stability. So N2 positive is going to be more stable than that of N2 negative. So remember this particular point as well. Am I clear? My dear students? Quickly in the chats. Am I clear? Yeah. At the same time, guys, one more thing. This was the order which I gave you. This was the order which is to be followed. Till the electrons are less or equal to 14. And let me tell you, this is the order which is to be followed when the electrons in the species are more than 14. Okay? Then this is the order to be followed. How to follow this? For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now degenerate. 11, 12, 13, 14. Okay? Again degenerate. 15, 16, 17, 18. Okay? Right? Then 19 and 20. Like this you are going to follow. And this particular order is to be followed till it is to be followed for those particular species which have got basically the electrons more than 14. Okay, which have got electrons more than 14. My dear students, one more important thing which I would want to tell you, because this is also asked. Whenever you talk about your isoelectronic species, isoelectronic species are the ones which have got same number of electrons. In case of isoelectronic species, you'll always find the bond order same. For example, if I talk about N2 and CO, right? N2, or wait, if I talk about, leave N2 aside, if I talk about, for example, NO positive and CO, let's say I need to check their bond orders. First of all, if I count electrons in NO positive, oxygen has got 8, nitrogen has got 7, so 8 plus 7 is 15, there is positive charge, 15 minus 1 is 14. So this is a 14 electron species. Similarly, 8 plus 6, this is also 14 electron species. So these two species, they have got same electrons. If they have got same electrons, that means they are isoelectronic. And when you have isoelectronic species, their bond order is same. And all your 14 electron species, their bond orders, as I've told you already, all the 14 electron species will have bond order of 3. Both the species will have bond order of 3. So remember, whenever you see isoelectronic species, their bond order is always going to be the same. Am I clear? Am I clear, people? Am I clear? Let me know once in the chats. And people, with this, we are done with the chemical bonding chapter, right? This was the most important, I would say super important chapter of your inorganic. Now comes one more chapter, and that's going to be your periodic classification. Periodic classification. My dear students, first of all, let me tell you, in this particular chapter, from which portion question comes. Let me tell you that first. Okay? In your periodic classification, the first topic comes in, the first question comes in, identification of period number, okay, group number, period number, group number, block number, and block. This is the first question which is asked from the periodic classification. The second question comes from atomic radius. The second question comes from this. The third question comes from ionization energy. Okay? And at the same time, the fourth question comes from your atomic radius, ionization energy, that is electron gain enthalpy. And after electron gain enthalpy, the last question comes from electronegativity. Okay? These are the topics which are to be covered in this particular chapter. Perfect. And from this chapter also, 2 to 3 questions can be asked. Okay, from this particular chapter also, 2 to 3 questions can be asked. So do you want to break here? And after that, we'll finish it? Because this is our last chapter. With this, your class 11th inorganic will be done. Do you want to break? Say yes or no, it's okay. Okay, it's 11:05 right now. So let me give the break till, have some tea or something, but only at one cost I'm going to give you a break. Are you guys going to be back on time? Because periodic classification will be done in, I think, 1.5 hours. That's it. And we are done. Tell me first of all, are you guys going to be back? Is that a promise? Write promise in the chats. Then I'm going to give you the break. Because guys, once I give the break, if you guys go, then it's no fun in teaching. It's no fun in teaching then. If I can stay, if I can stand for you guys, you have to be with me till the end too, right? And let me tell you, today I have already taken 10 offline classes from morning 8 till 5. I have taken some 10 offline classes. And after that, I was supposed to start the session at 7, but I was very tired. So I shifted the session to 7:30. Yeah. So from 7:30, we are continuing. And after this session, tomorrow morning again at 8, back to offline. And in the evening, back to online. Yeah. I think you should be working this much. You should be working this much instead of me. B block will be done in class 12th inorganic. Redox reaction will be done in class 11th physical. My next marathon is going to be class 11th physical. Okay, the right now time is 11:06, so let's be back. Break till 11:30 p.m. Okay, but please and please be back, everybody. Let me also have some coffee or something because I'm feeling dizzy. I'll be also back. See you in a while. So. Are you guys back? Yeah? Are you guys back? With the full Josh? Back with the full Josh? Yes. Back with the full Josh. Class 12th inorganic will be done in some days. Okay. Today was the time for class 11th inorganic. So we are going to finish it off. And by the way, the DPP which I'll be sharing with you, I think tomorrow or maybe tonight only after the session, try to solve that DPP. Huh? Atomic structure is not the part of inorganic, that is the part of physical chemistry. My next marathon is going to be class 11th physical, in which we'll be completing mole concept, redox, atomic structure, thermo equilibrium. Okay? That's going to be my next marathon. All right. Speak something in Tamil. Vanakkam. Did I say it right? Vanakkam, vanakkam. Where will I share the DPP? On my Telegram. Telegram channel is Wassim Bhat Chemistry Official. Wassim Bhat Chemistry Official is the Telegram channel name. When will be my next marathon? See, tomorrow it is Yavar Sir's marathon. Tomorrow is what day? It's Thursday Yavar, Friday HSP, Saturday will be Ambika's, Sunday it will be off. So Monday will be my next marathon. Monday will be my next marathon. Monday is going to be my next marathon, wherein I'll be taking a one shot of class 11th physical. That is the most important marathon, by guys. Okay, because in that marathon we'll be completing like mole concept, atomic structure, redox, equilibrium, thermo. 5 chapters. 5 chapters means, see, from equilibrium 4 questions, thermodynamics 4 questions, mole concept 2 questions, so 10, atomic structure 2, 12, redox 2. 14, 15 questions. Perfect. Should we start? Guys, Telugu, I do not know. Okay. See, I can understand a bit of Tamil because I've stayed in like Chennai for 5 years. I've done my college and stuff from Chennai only. Yeah. That's the reason I can understand a bit of Tamil. I can maybe speak a bit of Tamil as well. Yeah. What about the groups? The blocks, your E block, D and F, that is the part of class 12th inorganic, which is a separate marathon. Guys, I've already given you the schedule. You check that schedule. I've told you when to do what. Okay. Chalo, should we start? Should we start? Should we start? Should we start already? Should we start? Should we start? Everyone. This chapter is not going to take a lot of time. I think it will be done in like 1.5 hours only, or maximum 2 hours. Okay. Already? Quick, quick, quick. Give me some fire emojis in the chats. I want to get back with the same Josh. Quickly. Quickly, guys. I want to start and end with the same Josh, so have the same energy. Quick. Perfect, perfect, perfect. Perfect. So people, chalo then, let's get going. Let's get started. Let's have a look on, first of all, the modern period table. Okay, the modern period table, which is the long form of the period table. And every one of you would have already seen it, I'm pretty much sure. First of all, if you look at this particular period table, this is your group 1 and group 2. What do we call this particular block as? This particular block containing your group 1 and group 2 elements. What do you call them as? You call it as the S block elements. You call them as the S block elements, right? Group 13 till group 18. What do you call this as? You call it as P block elements. Okay? P block elements. From here to here, this particular block, as you can see, it is your D block, right? It's your D block. And this particular one, which is kept separately, what do you call this as? F block elements. You know it already, right? So your current modern form of period table, it is basically classified, right, into 4 blocks. S block, P block, D block, and F block, right? Why do we call this particular block as S block? Because in all these elements, the outermost electron that enters into the S subshell. In all these elements, the outermost electron enters into the S subshell. Similarly, why do we call it as the P block elements? Because in all these elements, the outermost electron that enters into the P subshell. Similarly, in all these elements, the outermost electron enters into the D subshell, right? Same goes for your F. Perfect. This is something which I believe every one of you would be knowing. Now, my dear students, certain things which you need to know. The modern periodic table, it is first of all based on your Bohr-Bury's electronic configuration. It is based on your Bohr-Bury's electronic configuration concept as well as the atomic number. You know, in your modern period table, elements are kept on the basis of their increasing atomic numbers. Okay? Number 1, in your modern period table, how many periods do we have? We have 7 periods, right? And we have 18 groups. 7 periods and 18 groups we have in the modern period table. This is again something which I believe every one of you would be knowing, right? Perfect. And similarly, in your modern period table, how many blocks do we have? We have got 4 blocks, SPDF. S block is that particular block wherein the last electron enters into. This is complete basics. Enters into the S subshell. Similarly, P block elements are the ones wherein the last electron enters into the P subshell. Similarly, D and F. This is some general information, my dear students, which I'm giving you. Now, the first block of elements which we have in the period table, that is your S block elements. And group 1 and group 2. This is your group 1 and this is your group 2. Group 1 and group 2 combinedly, what do we call them as? Group 1 and group 2 combinedly are called as your S block elements, right? And let me tell you, your group first elements, what do you call them as? You call them as the alkali metals. You call them as the alkali metals. And your group second elements, which is beryllium, magnesium, calcium, strontium, barium, right? You call them as the alkaline earth metals. You call them as the alkaline earth metals. Okay. My dear students, what is the general outermost configuration of alkali metals? It is NS1. The general outermost configuration of alkaline earth metals is NS2. Since group 1 and group 2 combinedly, what do we call them as? We call them as S block elements. So what is going to be the general outermost configuration of the S block elements? It is NS1 to 2. This is the general outermost configuration of your S block elements, which you guys are going to remember. That's all. Point number 1. Point number 2. If you look at your P block elements, group 13, this is group 14, this is group 15, group 16, group 17, group 18. So from 13 to 18th group, what do we have? We have got P block elements. From 13 to 18, what do we have? We have got P block elements. And one thing which I would want you guys to remember here, that is the outermost configuration of your P block elements, which is NS2 NP1 to 6. This is something which directly you guys are going to remember now. Okay? For example, let's say you have got boron. Okay? What is the outermost configuration of boron? It is 2s2 2p1. What is the outermost configuration of carbon? It is 2s2 2p2. Nitrogen, 2s2 2p3. Similarly, 2s2 2p4. 2s2 2p5. 2s2 2p6. Correct? For example, go a little down. In the boron family, if you go a little down, if the electronic configuration of boron is 2s2 2p1, the electronic configuration of aluminum is going to be 3s2 3p1. Similarly, here it's going to be 4s2 4p1, 5s2 5p1. If you talk about carbon, it's 2s2 2p2. Silicon is going to be 3s2 3p2. Similarly, this is 4s2 4p2. Talk about nitrogen, it is 2s2 2p3. 2s2 2p3, right? If this is 2s2 2p3, then this is going to be 3s2 3p3, 4s2 4p3, and so on. Talk about your helium, it is 2s2 2p6. This will be 3s2 3p6. This will be 4s2 4p6, and so on. So basically, the general outermost configuration of your P block elements is nothing but it is NS2 NP1 to 6. Basically, for group 13, it's going to be NS2 NP1. For group 14, it's going to be NS2 NP2. For group 15, it's going to be NS2 NP3. Similarly, it will go on, and for group 18, it's going to be NS2 NP6. So combinedly from group 13 to 18, what do we call them as? P block elements. And in case of P block elements, the general outermost configuration is going to be NS2, NP can be 1 to 6. This is the general outermost configuration of your P block elements. Perfect. This is something which I would want every one of you to remember. Okay. Similarly, when you talk about your D block elements, what is the outermost configuration of D block elements? Just remember it directly. N minus 1, D 1 to 10, and NS 0 to 2. This is the outermost configuration of your D block elements, which you will be remembering directly. And same goes for your F block elements. This is N minus 2, F 1 to 14, N minus 1, D 0 to 1, and NS 2. This is the general outermost configuration of your F block elements. Perfect. Right? Okay. Now, my dear students, now I'm moving on to our first topic. This was the general information. This was the general information. Sir, helium configuration is 1s2. Did I write something wrong? Just a second. Oh yeah, wait. This was helium. I was talking about neon basically. Okay, I was talking about neon. All right. Yeah. Helium is 2s2, absolutely. But when you talk about your neon, neon is what? Neon is 2s2 2p6. So this is going to be 3s2 3p6. This is going to be 4s2 4p6, and so on. Okay, now it's clear. All right, guys. The first topic with which we are starting the chapter. What is that? That is going to be prediction of the period number and group number. How can we predict? How can we predict the period number and the group number of the element? How can we predict in which period an element belongs to and in which group the element belongs to? In which period element belongs to and in which group the element belongs to. My dear students, first of all, we'll get to know the period number. We'll get to know the period number and the group number from electronic configuration. What if electronic configuration of an element is given? What if electronic configuration of an element is given? And from the electronic configuration, we have to identify the period number. How do we do that? Remember, my dear students, period number is nothing but it is the highest value of principal quantum number. Period number is nothing but it is the highest value of principal quantum number. If you have a look, let's say you have got the element whose outermost configuration is this 3s2, 3p6. What is the highest value of principal quantum number here? It is 3. So I would say the element whose electronic configuration is given, its period number is 3. Similarly, let's say you have got the element whose electronic configuration is given to us. What is the highest value of principal quantum number? That's 4. So this element belongs to period number 4. This is one more element whose outermost configuration is given. What is the highest value of principal quantum number? It's 5. So this particular element belongs to period number 5. Right? Period number 5. Horizontal rows are called as periods, right? And vertical columns, they are called as groups. I hope you know that. Horizontal rows are called as periods and vertical groups are called as group. Vertical columns are called as groups. Right? Right, people? So first of all, remember, whenever you have to check the period number of the element, if its electronic configuration is given, then check the highest value of principal quantum number. Whatever is the highest value of principal quantum number, that is going to give you the period number of the element. Number 1. Number 2, how do you get the group number of the element from the electronic configuration? How do you get the group number of the element from the electronic configuration? My dear students, in case of S block elements, group number is always equal to number of electrons in ns orbital. Number of electrons in ns orbital. For example, you have got the element whose outermost configuration is this. This is the electronic configuration of the element. Look at the ns. ns is containing how many electrons? ns is containing only 1 electron, right? So this particular element belongs to which group? This particular element belongs to first group. Number 1. If I ask you what is its period number? Its period number is 4. Highest value of principal quantum number. That's 4. Let's say this is one more element whose electronic configuration is given to me, right? So check how many electrons are there in ns. There are 2 electrons. So this particular element belongs to group number 2. This particular element belongs to group number 2. Now, highest value of principal quantum number is 5. So I would say the period number to which the element belongs to, that's 5. Again, simple and basic thing. So for S block elements, your group number is always equal to number of electrons in ns orbital. In case of your P block elements, how to check the group number? Group number is equal to 10 plus sum of ns and np electrons. 10 plus sum of ns and np electrons. For example, let's say you have got the element whose electronic configuration is 4s2, 4p6, outermost configuration. This is the outermost configuration of some element. Okay. First of all, it's a P block element because the outermost electron is in P subshell. It's a P block element. First of all, its period number is going to be 4. Its period number is going to be 4 because the highest value of principal quantum number is 4. Now, what about the group number? Group number is going to be 10 plus sum of ns and np. 6 plus 2 is 8. So 10 plus 8 makes it 18. So this particular element whose electronic outermost configuration was given to us, its group number is 18, right? Can you tell me what is going to be the period number of this particular element whose outermost configuration is given? Its period number is 3. If I ask you about its group number, it's again a P block element. So 10 plus ns plus np. 5 plus 2 is 7. So 10 plus 7 makes it 17. So this particular element belongs to 17th group. Okay? As simple as that. As simple as that. So this was for your P block elements. Now, my dear students, for your D block elements, group number is equal to sum of n minus 1d electrons and ns electrons. sum of n minus 1d electrons and ns electrons. If you look carefully, let's say you talk about iron. You talk about iron, right? The last electron has entered into the d subshell. The last electron has entered into the d subshell, right? The last electron has entered into the d subshell. Okay. So first of all, this is the d block element. It is the d block element, number 1. If I ask you what about its period number? Its period number is going to be highest value of principal quantum number, that's 4. If I ask you what about its group number is equal to sum of n minus 1d and ns. See, this is your ns and this is n minus 1d. ns contains 6 electrons. ns contains 2 electrons. n minus 1d contains 6 electrons. So 6 plus 2 makes it 8. So this particular element belongs to 8th group, right? This particular element belongs to 8th group. And if you talk about your F block elements, all your F block elements, be it your lanthanoids, be it your lanthanoids or actinoids, they belong to which group? They belong to group 3. They belong to group 3. For example, I'm randomly giving you an element whose atomic number is, for example, 67. Whose atomic number is 67. Is 67 lying in between? Yes. Right? So this is basically your lanthanoids. These are your actinoids. And your lanthanoids and actinoids, they comprise of what? Your F block elements. And all your F block elements, they belong to which group? They belong to your 3rd group. Perfect. This is again one important thing which I would want every one of you to remember, because anything can be asked from this. So this was identification of period number and group number. Period number and group number when electronic configuration is given to us. My dear students, what if electronic configuration is not given? What if atomic number is directly given? What if atomic number is directly given? What do we do at that point of time? What if atomic number is given and from the atomic number you have to check the period number and group number of the element? Again, there are few things which you have to remember. Again, just give me a second, guys. There are some spammers coming. So wait. Okay, now it's fine. All right. How do we check the period number and group number of an element whose atomic number is given? We got to know how to check the period number and group number from the electronic configuration. Now, how to check the period number and group number from the atomic number? My dear students, identification of period from atomic number. Identification of period from atomic number. Remember, if atomic number of the element is lies in this category, 58 to 71. If atomic number of the element lies in this category, 58 till 71, right? So 58 to 71 means your lanthanoids, and they belong to which period? Remember, your lanthanoids, they belong to 6th period, right? Similarly, if the atomic number of the element lies in this particular category, 90 to 103, that means the element belongs to your actinides, and your actinides, they belong to which period? They belong to 7th period. They belong to 7th period. Okay? In short, you have to remember this. These are the things which you have to remember, because it can be asked. 58 till 71, 6th period element. 90 to 103, 7th period element. Now, if atomic number of the element neither belongs to this category nor belongs to this category. If atomic number of the element neither belongs to this category nor belongs to this category, then period number of that element is always equal to period number of next inert gas. What does that mean? First of all, these are your inert gases. Helium, neon, argon, krypton, xenon, radon, right? These are your inert gases. Perfect. And my dear students, these are the atomic numbers. These are the atomic numbers of these inert gases. Helium belongs to 1st period, neon 2nd period, argon 3rd period, krypton 4th period, xenon 5th period, radon 6th period, right? Let's say I have got the element whose atomic number is what? Whose atomic number is 44. Let's say I've got the element whose atomic number is 44. 44 neither lies in this category nor it lies in this category, right? And if atomic number neither lies in this category nor in this category, then period number is equal to the period number of next inert gas. So for that particular element whose atomic number is 44, right? What is the next inert gas after 44? After 44, the next inert gas is 54. The next inert gas is xenon, whose atomic number is 54, right? And this xenon, it belongs to period number 5. That means this particular element also belongs to period number 5. Let's say you've got the element whose atomic number is 32. 32 neither lies in this category nor lies in this category. So period number is going to be equal to the period number of next inert gas. So what is the next inert gas after 32? It is 36, that is krypton. Krypton belongs to 4th period, right? Krypton belongs to 4th period. So this particular element whose atomic number is 32, it also belongs to 4th period. I hope I'm clear. I hope I'm clear with this. I hope I'm clear with this. Yeah? Is that clear, guys? Is it clear till here? Let me know once in the chats. Let me know once the chat's quick. Now comes one more point. How do we identify the group number from the atomic number? We know how to check the group number from electronic configuration. Now the point is, how do we check the group number from the atomic number? From the atomic number. Have a look. Again, there are few points. If atomic number of an element, which I'm representing with Z, if atomic number of an element belongs to this category or this particular category, then we already know the element belongs to which group? It belongs to third group. It belongs to third group. So we are talking about the F block elements. Let's say the atomic number of an element is 63. 63 lies over here. 96 lies over here, right? So both these elements, they belong to group 3. They belong to group 3. Okay? They belong to group 3. If atomic number of the element lies in this category, 104 to 118, 104 to 118. If atomic number of an element lies in this category, 104 to 118, then group number is equal to last 2 digits. Group number is equal to last 2 digits. For example, you have got the element whose atomic number is, for example, 110. 110. 110 lies in this category. What are the last 2 digits? 10. So group number of this particular element is going to be 10. Group number of this particular element is going to be 10. Let's say you have got the element whose atomic number is 112. 112 also lies in this category. So last 2 digits gives you the group number. So group number here comes out to be 12. Okay. Group number here comes out to be 12. Now, my dear students, if atomic number of the element neither lies in this category nor lies in this category, if atomic number of the element neither lies in this category nor lies in this category, then how do we calculate the group number? It is equal to 18 minus next inert gas minus atomic number. What does that mean? Have a look. For example, you have got the element whose atomic number is how much? 44. Let's say you have got the element whose atomic number is 44. 44 neither comes in this category nor comes in this category. Okay? 44 neither comes in this category nor comes in this category. Then I would say group number of the element whose atomic number is 44 is equal to 18 minus. What is the next inert gas? What is the next inert gas atomic number after 44? That is 54. Okay? Minus. What is the atomic number Z? That is 44. 54 minus 44 comes out to be 10. 18 minus 10 comes out to be 8. So the element belongs to what? The element belongs to 8th group. Element belongs to 8th group. Right? Perfect. My dear students, for example, you have got the element whose atomic number is 32. 32 neither comes in this category nor comes in this category. Then group number is going to be equal to 18 minus. What is the next inert gas after 32? It is going to be 36 atomic number, right? Minus, what is the Z value? Z value is 32. 36 minus 32 is 4. 18 minus 4 comes out to be 14. So this particular element whose atomic number is 32, it belongs to group 14. It belongs to group 14. I believe this is clear to everyone. Yeah? Right? So this is how we identify the period number and the group number of the element from electronic configuration as well as the atomic numbers. And guys, you have to remember these things, okay? You have to remember these things. Is this clear? Let me know once in the chats. Is this clear? Is this clear, people? Everyone. All right. Now, let's move on. There is something called as shielding effect. I hope you know it. Have you heard about shielding effect? Let me give you the slight idea of what shielding effect is all about. Let me give you the slight idea of what shielding effect is all about. My dear students, in simple ways, the decrease in the force of attraction on valence electron, due to the inertial electrons is called as shielding effect or screening effect. What does it mean? Have a look. For example, this is the nucleus. This is the nucleus, okay? This is the outermost shell, which contains an electron. So first of all, this nucleus would be attracting this electron towards itself by some force. This nucleus would be attracting this electron towards itself by some force. Okay, by some force. Now, my dear students, let's say there is one inner shell also, which also has electrons. For example. If the inner shell has electrons, can I say between these electrons there will be repulsions? There will be repulsions between these electrons. Due to the repulsions caused by the inner shell electrons, the force with which nucleus should have attracted this outermost electron towards itself. The force with which nucleus should have attracted the outermost electron towards itself. That force of attraction would be less because these inner shell electrons are exerting repulsions to this particular electron. Okay? Are you getting what I'm trying to say? I'm giving you the simplest way of understanding this. See, basically, due to the inner shell electrons, the force of attraction experienced by this particular electron, that decreases due to the inner shell electron. And that decrease in the force of attraction, on valence electron, due to the inner shell electrons, that decrease in the force of attraction you can call as your shielding effect. So basically these inner electrons, they are technically shielding this particular electron. They are shielding this particular electron. Now, my dear students, shielding is basically of two types. One is called as effective shielding, good shielding by the inner electrons. One is ineffective shielding. If shielding done by the inner electrons is more, that means force of attraction on this outer electron will be less. What does that mean? That means effective nuclear charge is less. Okay? Effective nuclear charge is less. If shielding is ineffective, if they are not shielding properly, force of attraction experienced by this electron would be more. That means effective nuclear charge is more. Remember these 2 points as well. One is called as effective shielding, one is called as ineffective shielding. Due to effective shielding, effective nuclear charge decreases. Due to ineffective shielding, effective nuclear charge increases. That's more. Okay? Is this point also clear? Let me know once in the chats if this point is clear. Due to effective shielding, due to good shielding, force experienced by this particular electron, the force of attraction experienced by this particular electron will be less, right? Right, people? If the shielding done by the inner electrons is ineffective, if it's not good shielding, if it's not proper shielding, that means this electron will be experiencing more force from the nucleus. That means effective nuclear charge is more. I hope this is clear. I hope this is clear. My dear students, two things which I would want you guys to remember. Effective nuclear charge is directly proportional to positive charge, inversely proportional to negative charge. What does that mean? See, let's say you have got certain species here, N positive, N and N negative. These are few species. Perfect. These are few species. I have to check among these three which one has got more effective nuclear charge. Wherein, among these three, wherein the outer electron will be experiencing more force from the nucleus. Among these three, wherein outermost electron will be experiencing more force of attraction from the nucleus. Simple, remember one thing. Effective nuclear charge, it is directly proportional to positive, inversely proportional to negative. So more the positive, more the effective nuclear charge. Here you have got positive charge, right? More the positive charge, more the effective nuclear charge, right? Similarly, more the negative charge, lesser the effective nuclear charge. So this is going to be the order of Z effective here. Simple. Simple. These are some basic things which I'm telling you. Some basic things which I'm telling you. For example, these are the species over here. These are the species over here. I have to arrange them on the basis of Z effective. More the positive charge, more Z effective. More the positive charge, more Z effective. Okay? So this H negative will come at the end. Let's say these are few more species, right? These are few more species which we have. More the positive charge, more the positive charge, more Z effective. More the negative charge, lesser the Z effective. Okay? So in short, Z effective is directly proportional to positive charge, inversely proportional to what? Inversely proportional to negative charge. Remember this particular point because I'll be using it. Tell me the answer of this question. What do you think? Tell me the answer of this question. In sodium atom, sodium, atomic number 11, right? 1s2, 2s2, 2p6, 3s1. Okay? In case of sodium atom, screening of 3s is due to what? Screening of the valence electron is due to all the inertial electrons, right? So these basically inertial electrons, they will be screening this particular valence electron, right? So it's pretty much simple. It's going to be 1s2, 2s2, 2p6, right? I hope this is clear. I hope this is clear. Now, my dear students, let's talk about the atomic radius. Let's talk about the atomic radius, the trends, and some things which you get from this. This is important. Okay, this is important. Atomic radius. How do you define atomic radius in simpler words? The radius of the atom. Radius of the atom. In simpler words, right? In simpler words. Right? Now, my dear students, atomic radius I classify into many types here. Covalent radius, which is defined for your non-metal atoms, right? Which is defined for your non-metal atoms. And you know non-metal atoms, they are covalently bonded. They are covalently bonded. Then comes your metallic radius. Okay, this one more type. Your van der Waals radius, one more type. And ionic radius, that's one more type. So let's get to know about all of them one by one. First of all, what is your covalent radius? Covalent radius is first of all defined for your non-metal atoms, right? Covalent radius is defined for your non-metal atoms, which are covalently bonded. Which are covalently bonded. Right? Few minutes back we discussed. A covalent bond is formed by the overlap of atomic orbitals into each other. A covalent bond is formed by the overlap of atomic orbitals into each other. So for example, let's say I've got for example a molecule A2. I've got the molecule A2. How exactly? Let's say this is a covalently bonded molecule. This is your A2 molecule. Okay, where the atomic orbitals have penetrated into each other. Okay, this is the nucleus of this atom and this is the nucleus of this atom. First of all, this particular distance, the distance between these two nuclei, the distance between these two nuclei is what you call as internuclear distance, is what you call as internuclear distance, which I'm representing with, for example, DAA. This is the internuclear distance. If I want to define the covalent radius, R covalent is going to be nothing. R covalent is going to be half of internuclear distance. R covalent is going to be nothing. It is going to be half of internuclear distance. Okay? Half of internuclear distance. Half of internuclear distance. When it comes to your metallic radius, for example, this is one metal, and in the metal, what do we have? These are the positively charged kernels. These are the positively charged kernels. Just a second, guys. There is some electricity issue. Okay. First of all, this is one. This is one. These are basically the positively charged kernels. Now, my dear students, first thing, let's say this is the nucleus, this is the nucleus. Okay. Between these two nuclei, the distance is called as internuclear distance. And again, if you do half of it, half of internuclear distance, half of, let me call this internuclear distance again as, for example, D. Again as D. Half of this internuclear distance is going to give you the metallic radius. Half of this internuclear distance is going to give you the metallic radius. If you have a look over here, in case of your covalent radius, these are the atoms which have merged into each other. These are the atoms which have merged into each other and formed a covalent bond. This distance between the two nuclei is called as internuclear distance, and half of internuclear distance gives you the covalent radius. Okay, number one. Number two, if you talk about the metallic radius, this is the internuclear distance between these two kernels, and make half of it, that is going to give you the metallic radius. Now, if I ask you, among covalent radius and metallic radius, which one is going to be more? When it comes to your covalent bond, atoms are merged into each other. So, internuclear distance in covalently bonded molecules is less. If internuclear distance in covalently bonded molecules is less, that means covalent radius will be less. Okay? So, remember, when you want to compare your covalent radius and metallic radius will be definitely more than that of covalent radius. Okay? Because when I defined the metallic radius, I showed that the atoms are just touching each other. Or I would say the area of overlap is very, very, very less. Here, the atoms are merging into each other. Right? Here, the atoms are merging into each other. Here, I would say the internuclear distance is less. Here, comparatively, internuclear distance is more. Half of internuclear distance gives you the radius. Right? So, here the radius will be less. Here, the radius will be more. Right? So, this is one point which you need to remember. Perfect. Metallic radius, that is always more than that of your covalent radius. This again one important point which you should remember. Now, when it comes to the van der Waals radius. First of all, van der Waals radius, it is defined. Van der Waals radius is defined for noble gases as well as the gaseous molecules present in solid state. See, this is your neon, noble gas, right? This is one more neon. Perfect. Perfect, guys. This is neon as well as this is neon. Perfect. My dear students, between these two neon atoms, there is van der Waals force of attraction, a weak force of attraction between them. There is a weak force of attraction between them. First of all, the distance between these two, when you calculate it, and when you do half of it, what does that give me? That gives me R van der Waal. One thing which you need to remember over here, if I ask you among your van der Waals radius, metallic radius and covalent radius, which radius will be more? Just one thing you have to remember. Your van der Waals radius is going to be maximum. Followed by metallic, followed by your covalent radius. Okay? This is one point which you have to remember. And similarly, if I ask you, how do you define the ionic radius? Ionic radius means radius of the ion. Ionic radius means radius of the ion. Ionic radius means simply radius of one ion. And here, just remember few points. Here, just remember few points. Here, just remember few points. For example, you have got the atom A. Now you are taking, let's say, one electron out of it. When you take one electron out of it, it becomes A positive. Okay. Now if you compare A and A positive, I would say here the effective nuclear charge is more. Here the effective nuclear charge comparatively is less. Correct? If more is the effective nuclear charge, that means the outermost electron is experiencing more attraction. That means size will be less. So can I say size of cation is always lesser than that of the size of the parent atom? Size of cation is always lesser than that of size of its parent atom. Size of its parent atom. Remember this particular point? Similarly, my dear students, let's say you have got the atom B. You are giving it one electron. Let's say it's getting converted into B negative. Effective nuclear charge is inversely proportional to negative charge. Few minutes back we have discussed. So I would say the effective nuclear charge of B negative will be less, and here the effective nuclear charge is more. Here the effective nuclear charge is more, here it will be less, right? So what will happen? What will happen? Can I say, since the effective nuclear charge here is less, that means outermost electron is not experiencing much attraction. So size definitely would have increased. So I can directly say size of anion will be greater than that of size of its parent atom. Size of its parent atom. Remember this particular point as well. Size of anion is always greater than that of size of its parent atom. Okay? Right? Is it clear, guys? Is it clear till here? Is it clear? For example, we have got A positive, A di positive, A tri positive. Effective nuclear charge is maximum here. If effective nuclear charge is maximum here, if effective nuclear charge is maximum here, what will happen? What will happen? What is going to be the order of the size? What is going to be the order of size? More the effective nuclear charge, lesser the size. So A tri positive will have least size. A tri positive will have least size. Then that of A di positive. Then that of A positive. Then that of A. Right? Basic things I'm telling you, and these are actually basic things only. So you don't have to, use your brain a lot in these. These are some things which you all must be knowing already. I'm pretty much sure. Now guys, see, if you talk about sodium, you talk about sodium positive, you talk about sodium di positive. Let's say sodium positive, sodium di positive. First of all, more the positive charge, more the effective nuclear charge. More the positive charge, more the effective nuclear charge. More the effective nuclear charge, lesser the size. So this is evident. Na di positive will have least size, right? Na positive will have comparatively more size, and sodium will have maximum size. But remember, the size difference between Na and Na positive is significant. Size difference between Na and Na positive is significant. Why is that? Because in Na, if you see, there are 3 shells. In Na positive, 1 electron has been taken out from 3. There are only 2 shells. So in Na and Na positive, the difference lies in the shell, number of shells. Here you have got 3 shells. Here you have got just 2 shells, right? So of course, due to the difference in the shell, sodium will have significantly more size than that of Na positive. Okay? Is this point clear? Talk about Mg positive and Mg di positive. One thing is clear. Mg di positive has got more effective nuclear charge. More effective nuclear charge means least size. So Mg di positive has got least size. Mg positive has got comparatively greater size. Mg has maximum size. But remember, the size difference between Mg positive and Mg di positive, it is significant. Size difference between Mg positive and Mg di positive, it's significant. Why? Because if you talk about the outermost configuration of Mg positive, it is 3s1. When you take 1 electron out from here, that electron is being taken out from here, from this 3s. So now in Mg di positive, the configuration becomes 2s2, 2p6. The configuration becomes 2s2, 2p6. Here you had 3 shells. Here you just have 2 shells, right? Here you have 3 shells. Here you just have 2 shells. So that is the reason size difference between these two is significant. Okay? I believe this particular point is also clear to you. Now tell me one thing. Tell me one thing. You tell me. X negative, X di negative. More the negative charge, lesser the effective nuclear charge. So this one will have least effective nuclear charge. Least effective nuclear charge. Least effective nuclear charge means very less force of attraction between nucleus and the outermost electron. Right? So size would have increased. Perfect. So if you compare their size, X di negative would have maximum size, followed by X negative, followed by X. Right? In simple words. Nothing else you are going to remember. Okay. For example, you have got O negative, O di negative. Talk about size. Talk about size. O di negative will have maximum size. Right? Similarly, N negative, N di negative, N tri negative. More the negative charge, lesser the effective nuclear charge. If lesser is the effective nuclear charge, lesser is the attraction between nucleus and outer electron. Right? If lesser is the attraction between nucleus and outer electron, more will be the size. N tri negative will have maximum size. Guys, am I clear till here? 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 Say yes or no once in the chats quick. Am I clear till here? Say it in the chats quickly. Everyone. And all these points are, guys, questions, huh? All these points basically are questions. Now, many a times question has been asked from the topic isoelectronic species. Okay? Isoelectronic species. What are isoelectronic species? What are isoelectronic species? Isoelectronic species are the ones which have got same number of electrons. For example, N tri positive, 10 electron species. O di negative, 10 electron species. This is also 10 electron. All these are basically your 10 electron species. So they are isoelectronic. How do you compare size in isoelectronic species? Simple. How do you compare the size in isoelectronic species? Simple, my dear students. Size, or you can say your radius, that is inversely proportional to positive charge. Size is directly proportional to negative charge, inversely proportional to positive charge. That's it. Size is directly proportional to negative charge, inversely proportional to positive charge. More the negative charge, more the size. N tri negative will have maximum size here. That's it. Okay, just remember this point. That's it. Nothing else you have to remember. Don't use your brain a lot. Okay, so people, more the negative charge, more is going to be the size of the isoelectronic species. More the positive charge, lesser is going to be the size, because inversely proportional. Just remember this particular point. That's more than sufficient. And from this particular topic, many a times questions have been asked. Many a times. Now, what is the general trend? What is the general trend when it comes to atomic size? My dear students, when you go from left to right in the periodic table, atomic size, or you can say atomic radius, decreases. When you move from top to the bottom in the periodic table, atomic size or atomic radius, that increases. That is something which every one of you would be knowing. Now, the point is on what factors your atomic size depends on, atomic radius depends on. When you have to compare the atomic radius of the elements which belong to the same period, whenever you have to compare the atomic radius of the elements which belong to same period, you will be doing that in terms of effective nuclear charge. You'll be doing that in terms of effective nuclear charge. On moving from left to right, what happens to effective nuclear charge? That increases. If effective nuclear charge increases, automatically force of attraction between nucleus and outermost electron, that increases. If force of attraction increases, that means size decreases. Perfect. So lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, they belong to same period. In the period, if you have to talk about the atomic radius, you'll be talking in terms of effective nuclear charge. On moving from left to right, effective nuclear charge increases, so size decreases. Right? So size decreases. This is evident. When it comes to the atomic radius in the group, when it comes to atomic radius in the group, okay, atomic radius in the group, talk in terms of number of shells. When you move from top to the bottom, shell number keeps on increasing. When shell number keeps on increasing, size, or you can say atomic radius, that automatically keeps on increasing. So lithium, sodium, potassium, rubidium, cesium, they belong to group first. When you move from top to bottom, size will keep on increasing, keep on increasing. So cesium has got maximum size in its group. Okay, in its group. I believe I'm clear to every one of you. Okay, I believe I'm clear to every one of you. Perfect. Right, guys? This is something which you have to remember. This is something which you have to remember. When it comes to your transition elements, my dear students, from scandium till manganese, remember, Z effective dominates over screening. Or just remember it directly, when you move from scandium to manganese, your size decreases. Then these are the three elements wherein what happens? Z effective and screening, they're almost equalized, due to which the size of these three elements is almost same. They've got almost the same size. They've got almost same size. But when you move from copper to zinc, remember, screening dominates over Z effective, or you can directly say size increases. Size increases. Remember this particular point as well. Okay? Remember this particular point as well. You can remember it in the form of a graph. From scandium to iron, atomic size decreases. Iron, cobalt, nickel, the size is almost the same. Then from copper to zinc, the size again increases. Size again increases. I hope I'm clear with this. I hope I am clear with this. Okay? I hope I am clear with this. One more thing, guys. One more thing. These are the points which are asked in the exam. And I'm not giving very detailed explanation of all of these. I'm just giving you that sort of information by means of which you can solve the questions. See, guys, this is your 3D series. This is your 4D series. This is your 5D series. When you move from top to bottom, when you move from 3D to 4D, see, leaving these three elements aside, don't talk about them. Talk about the rest of the elements. When you move from 3D to 4D, size increases. When you move from 3D to 4D, size increases. When you move from 4D to 5D, size almost remains the same. Size almost remains the same. Because if you see, from zirconium to hafnium, before hafnium, you have got 14 F block elements. Before hafnium, you have got 14 F block elements, wherein the last electron enters into the F subshell. Okay? And F subshell, what does it do? Effective shielding or ineffective shielding? F subshell, it does ineffective shielding. Due to ineffective shielding, size should decrease. See, basically, when you move from 3D to 4D, shell number increases, size increases. When you move from 4D to 5D, shell number increases, size should increase. But due to ineffective shielding, size should decrease. Due to which, from zirconium to hafnium, size almost remains the same. So leaving these three elements aside, when you move from 3D to 4D, size increases. When you move from 4D to 5D, size almost remains the same. Why not here? Because after this lanthanum, your F block elements start. Before this, F block elements do not start. They start after this. So here the general trend is there. Scandium, ytterbium, lanthanum, right? From 3D to 4D, size increases. 4D to 5D, size again increases in this particular group. Perfect. But in all the other cases, from 3D to 4D, size increases. From 4D to 5D, size almost remains the same. Is this point clear? Are you remembering these points? Are you remembering these points, people? Quickly in the chats. Yeah? Am I clear to everyone? I hope all of these things you guys are remembering properly. All right. All right. My dear students, if you talk about group 13 elements, boron, aluminium, gallium, indium, and thallium. These are your group 13 elements, right? See, in case of group 13 also, remember one thing. In case of a group 13 also, remember one thing. On moving from top to bottom, size should increase. Size should increase. So, aluminum has got more size than that of boron. But when you move from aluminum to gallium, what happens to size? Aluminum to gallium, what happens to size? Can you tell me? When you move from aluminum to gallium, what happens to size? What happens to size? It decreases. Why is that? Why is that? Because before gallium, there are some d block elements. You know, there are d block elements before gallium, where the incoming electron enters into d subshell. And d subshell, d orbital, they do ineffective shielding. Due to ineffective shielding, size should decrease. Right? Perfect. So remember this particular point because this one was asked in your NEET examination once. The correct order of atomic radius of group 13. The correct order of atomic radius of group 13. What is going to be the answer of this question? What is going to be the answer of this question? Quickly in the chats. Quickly. It's absolutely going to be option. It's going to be option D. Okay, remember this. Remember this. Remember this. Remember this one, guys. Gallium has got lesser size than that of aluminium because of the ineffective shielding of d electrons. But if you talk about the overall order, this is the overall order. Boron has got the least size, then comes gallium, then comes aluminium, right? Then comes indium, and then comes thallium. Remember this particular point. Okay? Can you tell me the answer of this question? Quickly. Can you tell me the answer of this question? First of all, this is calcium di positive. You have got K positive and argon. More the positive charge. More the positive charge, lesser the size. Right? More the positive charge, lesser the size. Few minutes back only we have discussed. Option B. Option B. Be di positive. First of all, beryllium. Hydrogen, helium, lithium, beryllium. Atomic number 4. So it should have 4 electrons. But there is di positive charge. So subtract 2 electrons. So there are only 2 electrons in Be di positive. Okay. So Be di positive is isoelectronic with. Be di positive is isoelectronic with which of the following ions? Be di positive is isoelectronic with which of the following ions? If you talk about lithium, lithium has atomic number 3, so it should contain 3 electrons. But if you talk about lithium positive, so subtract 1 electron, it also contains 2 electrons. So lithium positive and Be di positive, they have got same number of electrons, so they are isoelectronic species. their isoelectronic species. I hope all this is clear. Okay, what do you think about this one? What do you think about this one? Quick. Guys, this question has to be solved by you. Isoelectronic species order. More the positive charge, lesser the size. More the negative charge, more the size. That's it. More the positive charge, lesser the size. More the negative charge, more the size. Yeah? I hope all of this is very much clear. Now let's talk about one more term, that is your ionization energy. That's your ionization energy. Okay. My dear students, what is this ionization energy all about? Precisely, I'm going to tell you. Okay. And I'll show you all the types of the questions which can be asked here. First of all, it is the minimum amount of energy. It is the minimum amount of energy which is required to remove the most loosely bonded outermost shell electron. It is the minimum amount of energy which is required to remove the most loosely bound outermost electron from the isolated gaseous atom, or the isolated gaseous atom. Let's say I've got the gaseous atom M. This is the gaseous atom M, right? Now I have to remove the last electron here. This is the most loosely bound electron here. First of all, this electron is attracted by the nucleus for sure. I have to take this electron out. If I have to take this electron out, I have to break this force of attraction. And in order to break this force of attraction, I have to supply energy. The minimum amount of energy which is required to take out the most loosely bound valence electron when the atom is present in isolated gaseous form, that energy supplied is what you call as ionization energy. So basically, this is the isolated gaseous atom. I'm giving it the ionization energy. That means I'm taking the outermost electron out. Now it is getting converted into what? M positive. It's getting converted into M positive. Now, my dear students, let this ionization energy supplied be called as the first ionization energy. Now, for example, I have got M positive gas. I'm again giving it some energy and I'm taking one electron out. It is getting converted into M di positive. Okay. The amount of energy required to remove the electron from this M positive, that is your second ionization energy. Now, for example, your M di positive gas. Let me take one electron out from here so that it gets converted into M tri positive gas. Okay. And the amount of energy supplied here is what you call as third ionization energy. And remember, my dear students, ionization energy 1 is always less than that of ionization energy 2, less than that of ionization energy 3, and so on. Okay? Perfect. This is the order which you have to remember. First ionization energy is always least, followed by second, followed by third, and so on. This is the general order which you will be remembering. Now, what do you think are the factors which are going to affect the ionization energy? It's again pretty much simple. What are the factors which are going to affect the ionization energy? Guys, the first factor is again your effective nuclear charge only. First of all, whenever you are given with the elements which belong to same period, you have to compare the ionization energy of those elements which belong to same period. You are going to talk in terms of effective nuclear charge. It's pretty much simple. More the effective nuclear charge, more is going to be the attraction between nucleus and outermost electron. If more is the attraction between nucleus and outermost electron, that means more energy is required to take that electron out. More energy required means more is the ionization energy. Right? So in short, remember one thing, ionization energy is directly proportional to effective nuclear charge. And you already know effective nuclear charge, that is directly proportional to positive charge, inversely proportional to negative charge. Okay? Fe tripositive, Fe dipositive, and Fe. Fe tripositive has got maximum effective nuclear charge. So its ionization energy will be more for sure. Both are directly proportional. Okay, both are directly proportional. Now the second factor on which ionization energy depends on. What is that? Remember, my dear students, since you know your half-filled configuration and fully filled configurations. This is half-filled, P3 configuration, D5 configuration, F7, right? These are half-filled. P6, D10, F14, these are fully filled. Half-filled as well as fully filled configurations, they are very stable. They are very stable. If they are very stable, that means to take electron out from them, more energy is required. To take electron out from that configuration, which is more stable, more energy is required. That is the reason why in case of half-filled configurations and fully filled configurations, your ionization energy is more. For example, if we talk about nitrogen and oxygen, talk about this nitrogen and oxygen. Nitrogen's outermost configuration is 2p3. Oxygen's outermost configuration is 2p4. 2p3 means this is the half-filled configuration. 2p4 means 1, 2, 3, and 4. It is the partially filled configuration. Which one is more stable configuration? This is more stable. To take electron out from here, more energy is required. That is the reason the first ionization energy of nitrogen is always more than that of the first ionization energy of oxygen. Yeah? Am I clear? Am I clear, people? Am I clear? Yeah? Okay. If I talk about the second ionization energy, of nitrogen and oxygen, second ionization energy of nitrogen and oxygen, what do you think? The second ionization energy of nitrogen and oxygen. First of all, if I talk about the second ionization energy of nitrogen, that means I have to take electron from N positive. Here I have to take electron out from O positive. N positive means 2p2 configuration. O positive means 2p3 configuration. So basically I have to take electron out from this configuration. Here I have to take electron out from this configuration. Which configuration is more stable? This one. So to take electron out from this configuration, more energy is required. So I would directly say the second ionization energy of oxygen would be greater than that of nitrogen. Correct? Correct, people? I hope I'm clear to everyone. Am I clear? Let me know quickly in the chats, people, if all the things are clear. Let me know quickly in the chats if all the things are clear. What snap? Huh? Is anything wrong in taking the snap? So remember, the first ionization energy of nitrogen is more than that of oxygen, but the second ionization energy of oxygen is more than that of nitrogen. Yeah? All right. This is to be remembered. And right now, I was talking about those elements which belong to same period. Now, what if we have got the elements which belong to same group? For them, talk in terms of atomic size. It's pretty much simple. When you move from top to bottom, size increases. When size increases, the distance between nucleus and outermost electron, that increases. If distance between nucleus and outermost electron increases, force of attraction between them, that decreases. So lesser energy is required to take the electron out. So technically you can say, on moving from top to the bottom, then size increases, ionization energy decreases. So remember, in short, your ionization energy is inversely proportional to atomic size. So whenever you are given with the elements which belong to same group, talk in terms of size. Ionization energy inversely proportional to size. Okay? This is again pretty much simple, and I believe this is super clear to everyone. Okay? I believe this is super clear to everyone. Now guys, there is one more thing. There is one more thing which I would want to discuss with you. Let's say you have got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay? These are the elements which belong to same period. These are the elements which belong to same period, right? And in the period, how do we compare ionization energy? In terms of effective nuclear charge. On moving from left to right, effective nuclear charge increases. Effective nuclear charge increase means ionization energy increases. So what has to be the order of the first ionization energy? This is the expected order. This is the expected order. But is it the actual order? It is not the actual order. It is not the actual order. Why is that? If you talk about the outermost configuration of beryllium, it is 2s2. Outermost configuration of boron, it is 2s2, 2p1. Okay? 2s2 configuration, fully filled. 2p1 configuration, partially filled. To take electron out from here, more energy is required. That's why beryllium has got more ionization energy than that of boron. Now compare nitrogen and oxygen. This is something which we discussed a few minutes back. I told you a few minutes back, the first ionization energy of nitrogen is more than that of oxygen. Now this is not the expected order. Now it becomes your actual order. This is the actual order of your ionization energy. Am I clear? This is the actual order of your ionization energy, and this question has been many a times asked in your JEE examination. It can be asked in your NEET as well. Okay, it can be asked in your NEET as well. Perfect. All right, one more thing. Talk about your group 13 elements again. Boron, aluminium, gallium, indium, helium. These are your group 13 elements. These are your group 13 elements. Arrange them on the basis of their ionization energy. Arrange them on the basis of their ionization energy. Whenever you have to arrange the elements as per their ionization energy, which belong to same group, we talk in terms of size. We talk in terms of size, right? We talk in terms of size. Size order a few minutes back I gave you. Therefore, I'm directly giving you this particular point. This is the expected order. On moving top to the bottom, size increases. If size increases, ionization energy should decrease, right? So boron should have maximum, followed by aluminium, followed by gallium, followed by indium, followed by helium. But this is not the actual, it is expected. This is the actual order of ionization energy. You need to remember this particular point as well, because it can be asked. You need to remember this particular point as well. Okay? Okay, this particular point can be asked as well. This particular point can be asked as well. All right. Okay, one more thing. From 3D to 4D, size increases. Then from 4D to 5D. Then from 4D to 5D, due to the ineffective shielding of F electrons. Due to the ineffective shielding of F electrons. What do you think? When you go from 4D to 5D, what happens to ionization energy? Should it increase or decrease? You tell me. Should it increase or decrease? When you move from 4D to 5D, what happens to ionization energy? Should it increase or decrease? Of course, it's almost same, but whose is more? But whose is more? But whose is more? Remember, ionization energy of 5D will be more than that of 4D. Okay? Like you have got zirconium, hafnium, right? Hafnium has got more ionization energy than that of zirconium. Because this belongs to 5D, this belongs to 4D. All right, I hope these things are clear. Now, my dear students, there is one more thing. What are the applications of this ionization energy? Where do we use this? Where do we use this? What are the applications of this ionization energy? First of all, this ionization energy, we can talk about the metallic and non-metallic character in terms of this ionization energy. How exactly? Have a look. First of all, if you talk about metals, what do metals do? Metals are electropositive, right? Metals are electropositive. They lose electrons. Okay? So that metal, which has got low ionization energy, can lose electron easily. That metal, which has got low ionization energy, can lose electron easily. Right? So can I say metallic character that has to be inversely proportional to ionization energy? Lesser the ionization energy, easily electron can come out of the metal. Okay? So more is going to be the metallic character. In short. Pretty much simple. Similarly, if you talk about the reactivity of the metals, see, more easy if the electron is leaving from the metal easily. What does metal do? Metal loses electrons basically. When metal participates in some reaction, metals lose electrons. More the ease with which electron comes out, more reactive is the metal. Okay? More reactive is the metal. So simply remember one thing, reactivity of metals again is inversely proportional to ionization energy. Lesser the ionization energy, easily electron comes out. Easily electron comes out means more reactive is going to be the metal. So remember this particular point as well. Reactivity of metals, it increases down the group because ionization energy decreases. Okay? There is one more important point, guys. There is one more important point which I would want to discuss with you, because once question was asked in JEE from this, it might be asked in the NEET as well. You just have to remember one statement. See, talk about the sodium. When you take electron out from this, it becomes Na positive, and the energy required is what you call as ionization energy 1. Now take the electron out from this Na positive. Energy required is ionization energy 2. Okay? The difference between these two, I'm representing with delta I. That is, delta I means IE2 minus IE1. Okay? IE2 minus IE1. Remember, my dear students, this is important. Remember this particular point. If the difference between two successive ionization energies, is greater or equal to 16 volts, if delta IE, if the difference between these two successive ionization energies is greater or equal to 16 electron volts, then the lower oxidation state is stable. Lower oxidation state is more stable. First of all, how many oxidation states do you see here? This sodium has got +1 oxidation state. This sodium has got +2 oxidation state. If delta I, that means difference between successive ionization energies, it is 42.7 electron volts there, which is greater than 16 volts. That means the lower oxidation state will be more stable. Which is the lower oxidation state? +1. So Na positive would be more stable than that of Na +2. Right? This is one important point. If the difference between the successive ionization energies is more than that of 16 electron volts, that means the lower oxidation state is going to be more stable. Yeah? Perfect. Remember this particular point. And one more thing, guys. One more thing, and we are sorted. We are done with ionization energy. one more thing. If the difference between two successive ionization energies, if it comes out to be less or equal to 11 electron volt, if it comes out to be less or equal to 11 electron volt, see, this is ionization energy 1 and this ionization energy 2. The difference between the successive ionization energies, if it is less or equal to 11 electron volts, then remember, higher energy, higher oxidation states, they are more stable. So here, oxidation state is +1, here the oxidation state is +2. So Mg di positive would be more stable than that of Mg +1. Because if you see, the difference between the successive ionization energies here is 7.4 volts, which is less than 11 electron volts. Which is less than 11 electron volts. This is again one important point. Take a note of this. This is super important, guys. This I believe you can easily solve. Can you tell me its answer in the chats? This I believe you can easily solve. Yeah? What is the answer of this question? 2 minutes back only I showed you. Which one? Guys, this is something which I told you 5 minutes back only. I don't expect wrong answer here. Okay, so it's option 2 you are saying, huh? Lithium, boron, beryllium, carbon, oxygen. Yes, correct. It's option 2 only. Okay, it's option 2 only. This sort of a question is also asked. Look at it. This sort of a question is also asked. Look at it carefully. The first ionization energy is 7.1 electron volt. Second is 14.3. Third is 34.5. Fourth is 46.8. See guys what it means. The element is likely to be. The element is likely to be. Understand properly what I'm saying. In order to take first electron out, how much energy? 7.1 is required. In order to take second electron out, this much energy. In order to take third electron out, this much energy. In order to take fourth electron out, this much energy. In order to take fifth electron out, see the jump. See the jump here, it's more. So it is definitely indicating one thing. If this is the nucleus, that means the outermost electron has got 4 electrons. Outermost shell has got 4 electrons. To take first electron out, this much energy. To take second electron out, this much energy. Third electron out, this much energy. Fourth electron out, this much energy. Now fifth electron you have to take out. A lot of energy is required. That means fifth electron will be taken out from the inner shell. It has to be taken out from the inner shell. That's why the jump here is huge. So how many electrons are there in the last shell? 4 electrons. So there are 4 valence electrons technically. And in which of the elements there are 4 valence electrons? It is silicon, which contains 4 valence electrons. It is silicon which contains 4 valence electrons. Right? This sort of a question can also be asked. So remember it. Now guys, talk about your electron affinity. Electron affinity. Again, a simple thing and easy. Okay? Just remember it directly. What is it? It is the amount of energy which is released. It is the amount of energy which is released when an extra electron is added to the valence shell of the isolated gaseous atom. Okay? Is added to the valence shell of the isolated gaseous atom. Let's say this is your isolated gaseous atom. You are adding one extra electron to it. It is getting converted into X negative. The amount of energy released in this process is what you call as electron affinity, or you can call it as electron gain enthalpy. Okay? You can call it as electron gain enthalpy. Perfect. Now, my dear students, this is your, for example, electron affinity 1. Electron affinity 1, which is the first electron affinity is negative always. Okay? It is generally negative. Energy is released when first electron is added. But for example, imagine that you are adding one electron to X negative. It gets converted into X negative. When you add this electron to X negative, there will be repulsions. Perfect. So that's the reason second electron affinity is positive. Second electron affinity is positive. Perfect. So my point is Just this much. Generally, first electron addition of the isolated gaseous atom is exothermic process. Energy is released when first electron is added. Okay, energy is released during this process. Energy is released. That's why the first electron gain enthalpy, that's negative. The first electron gain enthalpy, that's negative. Perfect. But your second electron addition of the isolated gaseous atom is always endothermic. It's always endothermic. That means second electron gain enthalpy, that comes out to be positive. So if you talk about the successive ionization energy, successive electron gain enthalpies, let's say this was the isolated gaseous atom oxygen, giving 1 electron to it. How much energy is released? 141 kilojoules. Now, O negative plus 1 electron. Second electron gain enthalpy. Second electron gain, it will be positive, right? Similarly, third again will be positive. Third again will be positive. So basically, generally the first electron gain enthalpy is negative. Rest all the other successive ones, they are considered to be positive. What are the factors on which electron gain enthalpy depends on? What are the factors on which electron... Guys, we are almost done. Let's not take a break. We're almost done. It will be done in like 15 minutes. Okay, we'll be done in 15 minutes. All right? 15 to 20 minutes maximum. We are done almost. Don't worry. Okay. See, factors affecting electron affinity. My dear students, the first factor on which electron affinity depends on, that is atomic size. Lesser the size of the atom. Let's say this is one atom. This is one more atom. Perfect. This is the nucleus. This is the nucleus. I'm giving 1 electron to this. I'm giving 1 electron to this. Perfect. I'm doing electron addition to these atoms. Right? Here the size is less. Size is less. The force of attraction here will be more. More force of attraction means more energy released. So lesser the size of the atom, more is going to be the electron affinity. Okay? More is going to be the electron affinity. Remember it. Electron affinity and atomic size, they are inversely proportional. Number one. Number one. Electron affinity, it also depends on effective nuclear charge. It also depends on effective nuclear charge. More the effective nuclear charge, that means more is the tendency to gain 1 electron, to add 1 electron to the valence shell. Okay? Hence, more is the electron affinity, you can say. So it is directly related. Electron affinity and effective nuclear charge, they are directly proportional. They are directly proportional. Now, if you talk about the variation, variation here is pretty much simple. On moving from left to right, effective nuclear charge increases, so electron affinity increases because directly proportional they are. On moving from top to the bottom, it generally decreases. But, here is a case. If you talk about fluorine and chlorine, on moving from top to bottom, electron affinity should decrease. Right? Electron affinity should decrease on moving from top to the bottom. Right? It should decrease. So technically, fluorine should have more electron affinity than chlorine. But in reality, it's reverse. Chlorine has got more electron affinity than that of fluorine. Why? Because fluorine has got small size, more electron density, due to which the incoming electron experiences more repulsion. Right? That's the reason why electron affinity of fluorine is less than that of what? Is less than that of chlorine. Is less than that of chlorine. Okay. So guys, here are 3 things which can be asked in your exam. This is your group 17. Remember the order of electron affinities. This is your group 16. Remember the order of your... Okay, this is 16 as well as 15 combined. Okay. And remember this third one as well. Okay, remember this third one as well. Any of these orders can be asked. This is the most important one. Chlorine has got more affinity than fluorine, than bromine iodine. Here you have kept 16 elements as well as 15 elements. Okay, sulfur has got more. See, basically, if you talk about your fluorine and chlorine, if you talk about oxygen and sulfur, right? Chlorine has got more electron affinity than that of fluorine, and similarly, sulfur has got more electron affinity than that of oxygen. Now, if you want to compare the values of all of these, if you want to compare them, sulfur has got maximum, followed by oxygen, okay, followed by oxygen, followed by phosphorus, and followed by nitrogen. If you want to compare these basically. Okay. So technically, I would want you guys to remember them directly. No need to utilize a lot of your brain into it. What do you think is the answer of this question? This was asked in your JEE examination once, and it's a proper NEET standard question. This, I think you should be able to solve. If the electron gain enthalpy of Na positive, what does that mean? Electron gain enthalpy of Na positive. If the electron gain enthalpy of Na positive, okay, what is the value of electron gain enthalpy of Na positive? So we have to calculate electron gain enthalpy of this reaction. If ionization energy 1 of Na, ionization energy 1 of Na, that means from sodium you are removing 1 electron. From sodium you are removing one electron, getting converted into Na positive, right? So for this particular reaction, delta H is given to me as 5.1 electron volt. So this is the reaction for which delta H is given. This is the reaction for which delta H is to be calculated. Do you see these two reactions? Do you see this reaction is made when you reverse this, and when you reverse this, the sign of delta H will change. It will be minus 5.1. Right? It will be minus 5.1. Correct? It's again a simple concept. It's again a simple concept. Just reverse the sign and we are done. Just reverse the sign and we are done. Okay, one last term here. With that, we are done. So first of all, tell me, are all the things clear till here? Whatever things I've discussed? Tell me that, tell me that, tell me that. I know your brain is full. Just some 10 more minutes and we are done. 10 more minutes, please. Okay? At least you'll get that satisfaction. Yes, we have completed something. I want you to have that satisfaction. I want you to have that satisfaction. What is electronegativity? This is a very simple term. It is basically the tendency of the atom to attract the bonded pair of electron towards itself in a covalently bonded atom. For example, there's a covalent bond between A and B, right? Imagine B is more electronegative. What does that mean? B has got more tendency to attract the bonded pair towards itself, due to which electron density towards B will increase. If electron density towards B is increasing, which is represented by delta negative, and here it will be represented by delta positive. And due to electronegativity difference, what is happening? Polarity comes into play. Polarity comes into play. So basically, for example, you have got HCl molecule. Chlorine is more electronegative, right? So bonded pair will shift towards chlorine, or you can say electron density will shift towards chlorine, due to which chlorine gets delta negative, hydrogen gets delta positive, and this bond becomes polar. This bond becomes polar, right? What are the factors affecting this electron? What are the factors affecting this electronegativity? The first factor on which electronegativity depends on, that is size. Lesser the size, more is going to be the electronegativity. Okay? Lesser the size, more is going to be the electronegativity. On moving from top to bottom, size increases. Therefore, electronegativity decreases. On moving from top to the bottom, size increases. Therefore, electronegativity decreases. Fluorine, chlorine, bromine, iodine. On moving from top to bottom, size increases. So, electronegativity automatically decreases. Okay? First point. I'll be sharing this PDF as well, by the way. Second point, electronegativity, it depends on effective nuclear charge as well. That too directly proportional. More the effective nuclear charge, more is the electronegativity. For example, Mn di positive, Mn plus 4, Mn plus 7. This has got more positive charge, more Z effective. More Z effective means more electronegativity. O di positive, more positive charge. That means more Z effective. More Z effective means more electronegativity. Simple and basic stuff. So simple, remember, your electronegativity, it's directly proportional to effective nuclear charge. It is directly proportional to effective nuclear charge. At the same time, electronegativity is directly proportional to percentage S character as well. It is directly proportional to percentage S character as well. See, this carbon is sp3 hybridized. This carbon is sp2 hybridized. This carbon is sp hybridized. Which carbon has more S character? Which carbon has got more S character? I'll say this particular carbon has got more S character. And remember, more the S character, more is going to be the electron negativity. So this particular carbon will be definitely having more S character than that of this, than that of this. So remember, electronegativity is directly proportional to percentage S character as well, right? This is the point which you use a lot of times when it comes to your organic part, okay? And generally what happens? On moving from left to right, electronegativity increase. On moving from top to bottom, when size increases, electronegativity decreases. This is the general trend. This is the general trend, okay? Now guys, as I told you a few minutes back, if you remember, as I told you a few minutes back, what does metals do? They lose electrons. So, lesser the ionization energy, easily metal can lose electrons. That means more will be the reactivity of the metal. A few minutes back, I told you reactivity of metal, that is inversely proportional to ionization energy. When it comes to non-metals, when it comes to your non-metals, non-metals have got tendency to gain electrons. Non-metals, they have got tendency to gain electrons. So can I say more the electronegativity of the non-metal? Easily it will gain electron. And if easily the non-metal is gaining electron, that means more is its reactivity. What does metals do? Metals, they tend to lose electrons. Non-metals tend to gain electrons. More easily, if the non-metals are gaining electrons, that means more reactive they are. More easily, if the metals are losing electrons, that means more reactive they are. Again, I'm repeating the same thing. More easily, if the metals are losing electrons, that means more reactive they are. More easily, if the non-metals are gaining electrons, that means more reactive they are. So, non-metallic character is directly proportional to what? Electronegativity. More the electronegativity, more is going to be the non-metallic character. Third thing. Bond energy. The amount of energy required to break a bond, basically. The amount of energy required to break one mole of bond, basically, of a particular type. Anyways, I'm not going into the thermodynamics of it. For example, you have got HF, you have got HCl, you have got HBr, you have got HI. Where do you have to supply more energy to break the bond? It depends on the electronegativity difference. More the electronegativity difference, more is going to be the bond energy. As simple as that. More the electronegativity difference, more is going to be the bond energy. Say, hydrogen fluorine has got more electronegativity difference than that of hydrogen chlorine, than that of hydrogen bromine, than that of hydrogen iodine. Okay? So remember, more the electronegativity difference, more is going to be the bond energy. Similarly, my dear students, remember one more thing. Acidic strength of oxides. If you see, these are the oxides. Acidic strength of oxides as well as oxyacids. It is also directly proportional to electronegativity. More the electronegativity of the central atom, I would say, stronger the acidic nature is going to be. So this is B2O3, carbon dioxide, N2O5. This is boron, the central atom, carbon, the central atom, nitrogen, the central atom. So which one is more electronegative? Nitrogen, right? More the electronegativity, more is going to be the acidic strength of oxide or oxyacid. Okay, so this one is going to be more acidic. Here the central atom is chlorine, bromine, iodine. Which one is more electronegative? Chlorine. So this one is going to be more acidic. Okay, similarly, you have got sulfur, SET. Sulfur is more electronegative because sulfur, SET, they belong to same group. Down the group, electronegativity decreases. So this is more electronegative. More electronegative means this is going to be having more acidic nature. Right? This is going to have more acidic nature. So remember from now onwards, acidic strength of oxides or the oxyacids is directly proportional to what? It's directly proportional to the electronegativity of the central atom here. That's it. Okay? At the same time, acidic nature of the oxides, it is also directly proportional to the oxidation state of the central atom. Let's say, calculate the oxidation states. This is in maximum oxidation state, +7, maximum +5. Similarly, this will be +3. This will be +1. More the oxidation state of the central atom, more acidic the oxide is going to be. So this is going to be more acidic. H2SO4, H2SO3. This here sulfur is in +6 oxidation state. Here sulfur is in +4 oxidation state. When you calculate it, more is going to be the oxidation state, right? Stronger is going to be its acidic nature. So basically, whenever you are given with oxides, or oxyacids, first of all, check the electronegativity. More electronegative means more acidic. Then you can check the oxidation states. More the oxidation state of the central atom, more acidic it's going to be again. Okay? And my dear students, this is the last slide which you have to remember. Because any memory based question can be asked from this particular slide. Okay? Your basic oxides, basically your metal oxides, they form your basic oxides. Non-metal oxides are your acidic oxides. Examples of neutral oxides and examples of amphoteric oxides. Okay? These two are very important. Okay? All the oxides and hydroxides of these elements, they are amphoteric in nature. Any example can be asked from these. First of all, your metal oxides are basic in nature. Your non-metal oxides are acidic in nature. These are the examples of your neutral oxides, and these are the examples of your amphoteric oxides. I mean, all the oxides and hydroxides of these particular elements, they are amphoteric in nature. So, anything can be asked from this particular slide. This is very, very, very important, guys. Okay? So, with this, class 11 inorganic chemistry is done and dusted. And my dear students, I'm guaranteeing you one thing. Whatever points I've told you in the today's session, nothing apart from those points will be asked in your exam. That is my promise to you. Okay? That's my promise to you. Nothing apart from that. Okay? Perfect. So, in the comment section, what you guys are going to write? What you guys are going to write in the comment section? Class 11th inorganic chemistry done and dusted. Let me save these notes so that I can share these with you. IOC 11. Huh? Not in the chats. I don't want it in the chats. Right after the session, I want it in the comment section of the video. Okay? I want more than 100 comments in 10 minutes. Okay? That is going to be your cost of this session. That's something which you are going to pay me. Right? I want more than 100 comments in the comment section. Not here, not in the chats, in the comment section once the session ends. Perfect? Chalo, I'll be taking a leave with this. I'll see you in the next marathon, which is going to be on Monday, wherein I'll be discussing your complete class 11th physical chemistry. Okay? See you in the comment section.